Hello there, and welcome to Physics with William, where the questions are large, the voice is gentle, and the universe is allowed to unfold at a pace that does not demand very much from you at all. Tonight we're going somewhere extremely small. Not small in the way of a grain of sand or a speck of dust in a sunbeam, or even one of those crumbs that somehow survives every attempt at cleaning the kitchen table. Smaller than that by a truly unreasonable margin. We're going inside the atom. Now that is a curious destination because the atom is one of those things everybody has heard of, and yet very few of us spend our evenings picturing what is actually happening in there. We say matter is made of atoms, and that sounds tidy enough. It sounds as if the mystery has been wrapped up, labelled, and put away in a cupboard somewhere next to magnets, gravity, and all the other great invisible habits of nature. But that simple sentence hides an absurd amount of activity. Inside every chair, every glass of water, every loaf of bread, every book, every cloud, every cat, every person listening quietly in the dark, there is a hidden world of motion and structure and strange behaviour that does not resemble our everyday life in the slightest. The atom is not a tiny brick. It is not a little marble. It is not a neat miniature version of the world you already know. It is much stranger than that, and also, in its own way, much more interesting. Before we wander any further into that unseen territory, I would love to know where you're listening from tonight. Are you under a blanket with the lights off and the phone screen turned down low? Are you on a long train ride, looking out at the passing dark? Are you on a sofa, half awake, telling yourself you will rest your eyes for only a moment, which is one of the great optimistic stories humanity continues to tell itself? And while you're there, in your own little corner of the evening, take a moment and notice what is nearest to you. A pillow, a wall, a cup, your own hand resting still for once. Whatever it is, that ordinary thing is built from atoms. Your whole room is. You are. The calm air around you is. The fact that any of it feels stable and solid is already the first surprise in our story. If this sort of quiet wandering through physics helps you settle down, if it gives your thoughts something gentle to do while the rest of you starts to loosen its grip on the day, then a like and a subscription would be warmly appreciated. It helps this small, calm corner reach other people who might also enjoy a slower way of looking at science. And if not, that is perfectly all right too. You may simply lie there and let the words do what they can. So let us begin with the most familiar illusion of all. The world feels solid. It feels dependable. A floor is underfoot. A table stays where it was left. A mug resists your hand in a very firm and practical way when you try to place it down without enough care. We move through a world that seems packed with substance. This is wood. This is metal. This is skin. This is stone. But ask what any of those things are made of at the smallest useful level, and we arrive at the atom. And the atom, as it turns out, does not behave much like a tiny solid bead at all. That is one of the reasons this subject remains so irresistible. The closer we looked at matter, the less matter behaved the way we expected. At first, the atom was just an idea, a way of saying perhaps there is some final little piece that cannot be cut any further. That was the original spirit of it, a smallest unit, a last stop, a limit beyond which division simply stops being possible. It was a beautiful guess, and for a long time that was all it could be, because there was no way to peek inside. No one could hold an atom up to the light, no one could ask it to sit still, no one could politely request that it explain itself, and to be fair, if one could somehow interview an atom, I suspect it would be a terrible guest. Very evasive, constantly moving, not interested in clear answers, likely to respond to simple questions by becoming several possibilities at once. Which, as personalities go, is charming in fiction, but less helpful in measurement. Still, people kept asking, what is matter made of? Why do materials differ? Why does gold behave like gold, and oxygen behave like oxygen, and carbon seem to turn up absolutely everywhere, like the overachiever of the periodic table? There had to be some hidden order, There had to be some reason the world was not just one bland universal paste. And bit by bit, over centuries, the atom moved from philosophy into science. It helps, I think, to pause here and notice just how odd this is. Most of reality is never directly presented to us. We do not see atoms the way we see trees or doorways or the unfortunate state of the laundry chair. We infer them. We build evidence. We observe effects and work backward. We notice patterns in chemistry. We study gases, metals, light, electricity, radiation. We ask why substances combine in fixed ratios, why some materials conduct and others do not, why certain colours appear in flame tests, why matter has structure instead of chaos. And from all these clues, slowly, patiently, the atom emerges not as a guess anymore, but as the best explanation for a great many stubborn facts. Yet even once atoms were accepted, the picture was not settled. Far from it. The early atom was imagined as a tiny object, a little self-contained unit. Reasonable enough. But then came the discovery that atoms themselves had parts. Suddenly the final building block was not final after all, which is very typical of science, really. Each time we reach the bottom of something, nature calmly reveals a trapdoor. And that is where tonight becomes especially enjoyable. Because when we ask what happens inside an atom, we're not asking for one neat answer. We're opening a door into several layers of strangeness. There are tiny charged particles. There are powerful forces. There is motion that does not behave like ordinary motion. There are probabilities where you might have wanted certainties. There are flashes of light, little exchanges of energy, hidden structures, deep instabilities, and events taking place on scales so small that common sense starts to feel slightly underdressed for the occasion. Even so, the best way in is not to rush. It is to begin with something simple and close to hand. Consider your hand itself. It feels like a continuous thing. Smooth enough, solid enough, undeniably present. But your hand is made of cells, and those cells are made of molecules, and those molecules are made of atoms. Already the world is becoming layered. What feels continuous is built from parts. What seems still is full of motion. What appears compact is hiding a very different interior arrangement than the senses report. That is one of the quiet shocks of atomic physics. The everyday world is not lying exactly. It is just presenting the finished version. A polished surface, a convenient summary, very useful for getting through life, very poor at revealing what is going on underneath. Your senses were never designed to show you the atomic world. They were designed to keep you alive long enough to find food, avoid danger, and perhaps become needlessly attached to one particular mug. They are practical tools, not microscopic truth machines. So what is waiting underneath that smooth, practical summary? First, there is the simple fact that atoms are fantastically small. Small enough that if you tried to count them in a pinhead, you would be occupied for a period of time that would make geological eras look brisk. But size alone is not the main surprise. The surprise is arrangement. An atom is not a densely packed little pellet. Most of what we call an atom is not occupied in the ordinary sense at all. It is structured, yes. It is governed, yes. It is not empty in the everyday meaning of nothingness. But it is not solid the way a stone wall is solid. The centre is tiny and dense. Around that centre there is a region where the electron story unfolds. Already the old image of a miniature solar system begins to wobble, because that picture, while helpful for beginners, is only a rough starting place. The real thing is stranger and less obedient to ordinary intuition, and that raises a lovely question. If atoms are built in such an unusual way, then why do tables feel solid? Why can you not drift gently through the floor like a disappointed ghost? Why does your hand stop at the wall instead of continuing with an apologetic shrug? The answer lies not in atoms being little rocks pressed tightly together, but in the behaviour of their charged components and the rules that govern them. The solidity of matter is less like tiny billiard balls locking together and more like an immense and very disciplined negotiation between particles, energy and quantum rules. which is admittedly not how furniture advertises itself, but it is true all the same. What I find comforting about this is that the ordinary world remains ordinary while secretly being outrageous. Your lamp is still a lamp. Your blanket remains extremely convincing in its role as blanket. Tea continues to be tea, assuming you have not forgotten it and allowed it to become a historical document. But beneath all that familiar usefulness, the atom is doing things that no one would invent on purpose if they were trying to design a sensible universe from scratch. Take a breath for a moment and look again, mentally, at whatever object is near you. The edge of a desk, the sleeve of your shirt, the mattress beneath you. It seems calm, and in one sense it is. At our scale, stability has emerged. The object holds together, it performs its duties, it does not announce the astonishing internal story that allows it to exist. But the deeper truth is that this calm is built on activity. There are particles bound together, there are electrons occupying allowed states, there are interactions so rapid and so tiny that your senses never once report them, and yet they are the reason the world has shape, texture, chemistry, colour, and durability. This is perhaps the best doorway into the subject. The atom is not an obscure corner of physics, it is the backstage machinery of ordinary life. Ask why metals conduct electricity. Ask why salt dissolves. Ask why fire emits light. Ask why some elements are stable while others decay. Ask why stars can shine long enough for planets and life to exist. Again and again the path leads inward, toward the atom and beyond it. And perhaps that is why the topic feels so satisfying. It takes something familiar and reveals that familiarity itself is a kind of achievement. The world could have been chaos. Matter could have been unable to hold structure. Atoms could have been so unstable that nothing lasting ever formed. Instead, there is this rich balance of order and strangeness. Enough structure for stones, oceans, lungs, and language. Enough oddness to keep physicists employed and pleasantly puzzled. Of course, the atom did not yield its secrets all at once. Scientists had to tease the story out piece by piece. They found evidence that atoms contained negative charges. Then they discovered a central nucleus. Then they learned that the nucleus itself contained more than one kind of particle. Then those particles turned out to have deeper structure too. Each discovery made the atom less simple and more interesting. It was as though every answer came with a note attached saying, "Good start. Now look closer." That spirit is the one we will keep as we move forward. No hurry, no need to force it into one clean image too soon. The atom is best approached gradually, with a bit of patience and a willingness to let common sense be gently retrained. Over the next stretch of this journey, we will look at why the world that feels solid is built from components that are mostly not solid in any familiar way. We will look at the strange region where electrons belong, or perhaps belong is too confident a word. We will move toward the tiny dense centre and meet the particles gathered there. We will see why light gets involved, why some atoms hold together while others quietly fall apart, and why the deeper we go, the less the universe resembles the furniture showroom version of reality. For now, all we really need is this first shift in perspective. The ordinary object is not ordinary all the way down. Inside it is an architecture too small to see, and too strange to guess correctly without help. The calm surfaces around you are made of atoms. Those atoms are not inert little pebbles. They are organised systems with inner structure and hidden rules. And if the world feels stable tonight, that stability is not the absence of activity. It is the result of it. So as you settle a little deeper and the room grows quieter, let that thought rest somewhere in the background. The pillow, the sheet, the wall, the air, your own hand. All of it composed of unimaginably small arrangements. All of it built from atoms, each atom carrying a secret interior life that almost never announces itself in public. The universe is often like that, very dramatic underneath. perfectly composed at the surface. And once you begin to look at matter this way, another question arrives naturally. If everything around us is made from atoms and atoms are not solid little beads at all, then what exactly gives the everyday world its firmness, its texture, its resistance, its convincing sense of being there? That is where the story really starts to open, because the world that looks solid is doing something much more subtle than simply being packed full. That is the oddity, really. The world looks full, it looks packed. It looks as though matter has been poured into every object until there is simply no room left for anything else. A table appears dense, a wall appears dense, your own hand, resting quietly in front of you, appears dense. The impression is so immediate and so persuasive that it hardly feels like an impression at all. It feels like plain fact. The world is made of solid things. You learn that very early in life, usually by walking into one of them. Yet as soon as physics begins to look beneath the surface, that confidence starts to loosen. Not because the table stops being a table, or because the wall becomes less inconvenient in the night, but because the solidity we experience is not what it first seems to be. The surface story and the deeper story are not the same. At the scale of daily life, objects behave like continuous, stable, substantial things. At the atomic scale, what we call solidity turns out to be a kind of organized refusal, a rule-governed resistance, a consequence of structure and interaction. Matter does not feel solid because tiny bits of stuff are packed together like grains in a sack. It feels solid because the particles inside atoms and between atoms behave in ways that prevent easy intrusion. The world is not a heap of miniature stones. It is more like a vast system of boundaries. That may sound a little abstract at first, so it helps to stay with ordinary experience. Imagine placing your hand on a wooden desk. You feel pressure. You feel texture. Perhaps the wood is smooth, perhaps slightly rough, perhaps cool in a way that seems to belong to wood itself rather than to temperature. It feels direct. Your skin touches the desk. Simple. Immediate. But the deeper account is stranger than that. At a very small scale, the outer regions of the atoms in your skin and the outer regions of the atoms in the desk do not merge into one another. They interact. They push back. Forces between charge particles prevent the atoms from collapsing together. So the sensation of contact, which feels so clean and obvious, is actually the experience of microscopic resistance. That is one of the first great surprises waiting inside ordinary matter. What we call touching is not quite the same as two things blending into physical overlap. It is more like a negotiation carried out at unimaginably small distances. Your hand comes near, the atoms in your skin approach the atoms in the wood, and then the electric structure of those atoms says, in effect, this is close enough, no further. The result is a pressure that your nerves interpret as contact. The desk feels solid not because you and the desk become one continuous substance, but because nature has very strong opinions about where certain particles are allowed to be. There is something very satisfying about that, even if it sounds slightly impolite. The material world is not welcoming in that intimate microscopic sense. It is courteous enough to support you, useful enough to hold your lamp and your books and your cups of tea, but it is not interested in letting one object simply drift through another. The world has rules, strong ones, and solidity is one of the ways those rules become visible to us. Now, this does not mean the old everyday understanding is useless. Quite the opposite. For most human purposes, it is exactly right to say the desk is solid. Language is not failing, it is just giving the large-scale version. Physics then arrives and says yes, certainly, but let us be more precise about what sort of solid we mean. Because if you picture matter as tiny hard pellets pressed tightly together, you will miss the deeper mechanism entirely. What makes this more remarkable is that atoms are not little packed balls. Most of the space associated with an atom is not occupied by a dense lump of material in the way common sense expects. There is a tiny central nucleus, and then there are electrons, whose behaviour does not resemble little planets circling obediently in neat tracks, despite how often that image appears in classrooms. The atom is structured, but it is not compact in the way a pebble is compact. It is better understood as a region with a concentrated centre and surrounding patterns of electron behaviour. That alone should already make you suspicious of your first intuition. If the building blocks of matter are arranged in such an open and strange way, then the firmness of the world cannot be explained by simple crowding. And yet firmness is what we get. You can lie on a bed without passing through it. Your feet meet the floor and stop. A spoon keeps its shape. A stone resists your hand. Even the air, which we think of as loose and open, can push back hard enough in the right conditions to hold up a wing or rattle a window. Matter has resistance almost everywhere you turn. So where does that resistance come from? A great deal of it comes from electricity, though not in the dramatic thunderstorm sense. Atoms contain charged particles, and those charges matter enormously. Electrons carry negative charge. Protons carry positive charge. Charges influence one another. Like charges repel, opposite charges attract. This simple pattern, repeated throughout nature with extraordinary consistency, helps shape everything from chemistry to the way your fingers fail to pass through the table. The outer regions of atoms are governed by electrons, and when atoms are brought close together, those electron structures begin to matter very strongly. It is tempting to imagine two atoms as tiny round objects that meet like billiard balls. But billiard balls themselves are only solid because of the same atomic story. So bringing billiard balls in as an explanation would only delay the mystery, not solve it. Better to stay with the atom directly. When the electron regions of atoms are forced too close, the electromagnetic interaction becomes strongly repulsive. The particles do not simply allow unlimited compression. There is an increasing energetic cost. The closer you try to force matter together, the more fiercely matter pushes back. This is why a chair supports you. At the scale of ordinary life, your body is pressing downward under gravity, and the material of the chair responds by generating an opposing force. That upward support does not come from a hidden column of tiny rigid rods inside the chair. It comes from atoms and molecules shifting slightly, their internal electromagnetic relationships resisting deformation. Sit on a cushion and the structure yields a little. Sit on stone and it yields hardly at all. But in each case the same general principle is present. Matter can be compressed or bent or stretched only so much before its internal forces answer back. That answer back is what gives the world its tactile presence. Without it, objects would offer no resistance. There would be no surfaces in the familiar sense, no weight in the hand, no tension in a stretched string, no spring returning to shape, no ceramic mug stubbornly surviving until the exact moment it decides not to. Material properties depend on this hidden atomic discipline: elasticity, hardness, brittleness, flexibility. All of these words describe large-scale behaviour that originates in microscopic structure. Wood feels different from steel because the arrangement of atoms is different, the bonding is different, the response to stress is different. Rubber rebounds because its molecular structure allows certain kinds of stretching and return. Glass shatters because it does not deform in the same forgiving way before its structure gives way. Ice is slippery, not because it is simply frozen water and therefore obliged to be inconvenient, but because of the way water molecules organize themselves and interact at the surface. Matter is full of personality, if one may use that word carefully, and the source of that personality lies in atomic arrangement. The strangest part may be that our senses do not tell us any of this directly. They report outcomes. They say smooth, rough, hard, soft, cold, warm, heavy, light. Those are not illusions, but they are translations. Your nervous system is converting microscopic events into macroscopic experience. When your fingertip moves over polished stone, it is not perceiving atoms one by one. It is perceiving the collective effect of countless interactions, averaged into a sensation stable enough for a human brain to use. Reality arrives pre-interpreted. We are spared the full microscopic detail because if we were forced to deal with it consciously at every moment, even putting on socks would become an exhausting scientific conference. And there is another layer to this. The world does not just resist because of electrical repulsion. There are also quantum rules that matter, especially when identical particles are involved. Electrons are not free to pile into the same conditions indiscriminately. There are restrictions, deep and fundamental, on how they can be arranged. This contributes to the stability of matter in a profound way. It helps explain why matter occupies space in the persistent manner it does, why atoms form structured shells, why ordinary objects do not collapse into featureless density. The universe is not merely full of particles, it is full of particles obeying very specific rules about how they may coexist. One could almost say that matter remains matter because the particles are not allowed to behave carelessly. Nature is, at the smallest scales, surprisingly strict. There are permitted arrangements and forbidden ones. There are patterns that can exist and patterns that cannot. Out of that stern microscopic order comes the soft blanket, the wooden floor, the iron bridge, the loaf of bread, the paper page. The calm objects of daily life are the visible side of invisible discipline. It is worth lingering on how extraordinary this is. You press your palm to a wall and feel something simple. The wall stops you. But hidden inside that moment is an immense cascade of lawful behaviour. Electrons in the atoms of your skin and the wall interact. Forces rise sharply with closeness. The atomic and molecular structure of the wall distributes stress across trillions upon trillions of particles. Your nerves signal pressure. Your brain announces contact. All this takes place with such speed and reliability that it feels immediate and primitive, as though no explanation were needed. Yet the explanation is there, and it is astonishingly rich. Solidity, then, is not a basic ingredient poured into matter like a dye. It is an emergent experience, a large-scale consequence of smaller-scale behaviour. That phrase can sound more mysterious than it needs to, so let us keep it grounded. It simply means that when enormous numbers of particles interact under consistent rules, new stable patterns appear at our scale. Wetness is not found inside a single water molecule, but many water molecules together can be wet. A single grain does not make a heap, but enough grains do. Likewise, a single atom is not a tiny solid object in the everyday sense, yet countless atoms arranged in certain ways create the stable solidity we know. The whole world is full of such layered truths. A melody is not inside any one note. Traffic is not inside any one car. A crowd is not inside any one person. And solidity is not inside any one atom as a simple little chunk of hardness. It arises from relationship, arrangement, and rule. What feels full is often structured. What feels direct is often collective. Physics has a way of taking the obvious and revealing that it is only obvious from very far away. There is also a quiet comfort in this view, because it tells us that the familiar world is not separate from the strange world. The strange world is how the familiar world happens. These are not two universes awkwardly sharing the same address. They are the same universe seen at different scales. The bed you lie on is not ordinary on the outside and exotic somewhere else. It is exotic all the way through. It just behaves with wonderful steadiness when enough atoms work together. That steadiness matters. Were atomic forces slightly different, were the laws of particle behaviour not what they are, the macroscopic world might be unrecognisable. Matter might not form durable structures. Chemistry might be impoverished or chaotic. Solid objects, in the rich varied sense we know them, might never emerge. There might be no mineral hardness, no metal strength, no wood grain, no bone, no skin, no paper, no planets with crusts, no furniture for human beings to stub their toes on in the dark. The reliability of everyday matter is not guaranteed by logic alone. It depends on the actual workings of nature. Even the phrase empty space begins to change meaning here. We often hear that atoms are mostly empty, and while that phrase points towards something important, it can also mislead if taken too casually. Empty, in ordinary language, suggests nothing useful happening. No structure, no resistance, no significance. But the regions within and around atoms are not empty in that dull sense. They are governed domains. They are places where fields matter, where electron behaviour matters, where probabilities matter, where interactions decide what can and cannot occur. So when we say the atom is mostly empty, we are not saying it is mostly irrelevant blankness. We are saying the dense nucleus occupies only a tiny fraction of the atom's extent, while the rest is a more subtle kind of physical reality. And subtle reality is still reality. A staircase is real because it stops your foot, not because it satisfies an outdated picture of little packed bricks. Likewise, atomic structure is real because it produces consequences. It gives rise to chemical bonds, electrical behaviour, optical properties, pressure, rigidity, conductivity, colour. It builds the large-scale world from rules too small to see. The proof of the atom is not that you can glance at it in the way you glance at a lamp. The proof is that when you calculate and test and compare, the atom explains why lamps shine, why metals conduct, why glass can be clear, why salt dissolves, why materials differ, why matter holds together at all. Perhaps that is why the study of matter feels so rewarding. It takes the most familiar things and makes them new without making them alien. Your room remains your room. The blanket does not lose its usefulness because physics has entered the conversation, but it gains depth. The ordinary object acquires an interior life. The wall that once seemed merely there becomes the visible result of countless atomic interactions. The hand that once seemed a single, smooth possession becomes a marvel of structured matter held together by forces and rules so precise that they can sustain sensation, motion, memory, rest. You might even notice, if you let yourself, that the world becomes slightly more impressive after this shift. Not less comfortable, not more cold, just more intricate. The spoon on the bedside table is no longer a simple piece of metal. It is a triumph of atomic order. The fabric against your skin is a network of fibres, molecules, bonds, charges and constraints, all of it arranged in such a way that your brain may summarise the experience with one wonderfully lazy word: soft. And this is still only the beginning. Because once the firmness of matter stops looking simple, the next question becomes unavoidable. If the world gains its solidity from interactions between atoms and from the structure of atoms themselves, then we have to look more carefully at those atoms. We have to ask what their outer regions are really doing. We have to stop picturing electrons as tiny obedient beads and begin approaching them on their own strange terms. The solid world leads us inward. It always does. What seemed like the end of the mystery turns out to be the doorway to a deeper one. And as we move a little further into that hidden architecture, the next thing waiting for us is the place where electrons actually are. There is a phrase that gets used a great deal whenever people begin talking about atoms, and it is one of those phrases that is both helpful and slightly mischievous. We are told that the atom is mostly empty space. That sounds simple enough. It sounds almost disappointingly simple, as if the entire hidden architecture of matter could be summarised by the word empty, and then politely left alone. But the moment you sit with it for longer than a few seconds, the phrase starts to behave badly. Empty compared with what? Empty in what sense? Empty like an unused room. Empty like outer space. Empty like your fridge the evening before you finally admit you need groceries. Or empty in some stranger physical sense that ordinary language was never really designed to handle. Because if atoms are mostly empty, then why does the world not feel empty? Why does your hand not pass through the table? Why does the floor continue to perform its deeply appreciated duty of not letting you fall through it? Why does matter, built from things that are said to be mostly empty, present itself as solid, reliable, and almost aggressively present? That is the puzzle worth lingering over. The atom is mostly empty, yes, but it is also strangely full of structure, full of rules, full of influence, full of possibilities for where particles may be and what they may do. So when physicists say empty, they do not mean irrelevant blankness. They do not mean an abandoned void with nothing interesting going on. They mean that the dense material core of the atom occupies only a tiny region compared with the total extent of the atom. That is a very different statement. It is more precise, more useful, and much less likely to send the imagination wandering off in the wrong direction. The easiest way to feel the oddness of this is to begin where your instincts already are. If you picture an object, any object at all, perhaps the pillow beneath your head or the cup on the bedside table, you probably imagine it as being full all the way through. Not visually, of course, since you're not peering into it with some miraculous inner microscope, but conceptually. The thing seems filled with substance from surface to centre. If you sliced it in half, and then sliced it again and again, you would still expect each smaller piece to remain material through and through. That expectation is not foolish. It is how large-scale matter behaves, but the atomic story complicates it. At the deepest useful level for chemistry, and much of ordinary physics, matter is built from atoms, and atoms are arranged in a way that leaves a vast difference between where the mass is concentrated and the overall size of the atom. This realization did not arrive because someone sat very still one afternoon and guessed beautifully. It arrived because scientists learned how to interrogate matter in indirect but clever ways. One of the most famous moments in that story came when physicists began scattering tiny fast-moving particles at thin sheets of metal. The expectation, based on older pictures of the atom, was that these projectiles would mostly pass through with only gentle deflections, and most of them did. But every now and then one came bouncing sharply back, as if it had struck something unexpectedly concentrated and powerful. It was a deeply revealing inconvenience. The atom could not be a soft, evenly spread lump of positive charge with electrons floating around like raisins in a pudding. There had to be a tiny dense centre, a nucleus, something massive enough and charged enough to send the occasional incoming particle flying backward. That discovery changed the mental picture entirely. The atom was no longer a tidy little blob. It had a centre, and then an enormous amount of region around that centre, in which other important things were happening. If you were hoping the new picture would feel more intuitive, I'm afraid nature had other plans. Because a nucleus at the centre solves one problem and creates another. If most of the mass is packed into that tiny central region, then what exactly is the rest of the atom? Why does it matter so much? And why does something with such an apparently open internal layout contribute to the firmness of the world? It helps here to separate two different meanings that often get mixed together. One meaning is where the mass is. The other meaning is where the atom extends. These are not the same. Most of the mass of an atom sits in its nucleus, which is astonishingly small compared with the atom as a whole. But the atom is not just the nucleus. The atom also includes the regions associated with its electrons, and those regions determine much of the size, chemistry, and interaction of the atom. So when people say atoms are mostly empty, what they often mean is that the tiny nucleus takes up very little of the total atomic volume. That much is true, but the rest of the atom is not a pointless gap. It is the place where the electron story unfolds, and the electron story is the reason matter behaves the way it does. An analogy may help, provided we promise not to fall in love with it too much. Imagine a great cathedral with a single seed placed somewhere near the centre. If you asked where most of the dense material was, you would point to the seed. If you asked how much of the building the seed occupies, the answer would be almost absurdly little. Yet if the rest of the cathedral were filled with invisible but strict rules about where you could walk, where you could place your hands, how close you could come to certain zones, and what would happen if you tried to cross a boundary, then the building would not feel empty in any practical sense. The open space would still be full of consequence. The atom is somewhat like that, though far stranger and far less cooperative with architectural metaphors. The word empty misleads us because in daily life, empty means nothing there. An empty drawer contains no socks, which may or may not count as an improvement depending on your relationship with laundry. An empty room contains no furniture. An empty cup contains no tea, which is the gravest of the three. But at the atomic level, a region may be empty of dense nuclear matter, while still being a place where the presence of electrons matters, where electric interactions matter, where the structure of the atom is defined. A better phrase might be mostly not densely occupied, but that lacks charm, and physics, for all its virtues, has never been particularly good at naming things in a way that helps anyone sleep. So let us stay with the strangeness itself. Suppose you could somehow shrink down far enough to approach an atom in a meaningful way. You would not encounter a tiny billiard ball. You would not see a compact bead with a smooth, hard shell. You would find a tiny central nucleus, and then, beyond that, a region that does not behave like ordinary solid matter at all. The old classroom image of electrons circling like planets around a sun is not wholly useless as a first hint, but it becomes misleading very quickly. Electrons are not tiny marbles orbiting in neat visible tracks. Their behaviour belongs to quantum physics, and quantum physics is not interested in preserving your comfortable mechanical intuitions if it can possibly help it. Even before we get fully to electrons, though, the scale difference itself is worth admiring. The nucleus is remarkably small compared with the atom. So small that if the atom were enlarged to a size familiar to human experience, the nucleus would still remain tiny by comparison. The rest of the atom would not be packed with little chunks of matter. It would be an enormous region in which the atom extends, but in a very non-classical way. That is why the phrase mostly empty survives. It points to a genuine difference in scale, but again, scale is not the whole truth. The atom is mostly empty only if by empty you mean not filled with dense nucleus. It is not empty in the sense of physically unimportant or free of structure. In fact, some of the most important features of matter come from exactly those outer regions. Chemical bonding happens because atoms interact through their electrons. The size of atoms, the shapes of molecules, the way substances combine or refuse to combine, the reason oxygen behaves differently from neon, the reason carbon can build such extravagant structures. All of that depends not on the tiny nucleus alone, but on the arrangement and behaviour of electrons in the surrounding region. So the atom is a lovely contradiction. The place where the mass is concentrated is not the same as the place that gives the atom much of its interactive personality. The centre is tiny and heavy. The outer regions are light and expansive and crucial. This is why the world can be built from atoms that are mostly empty and still feel absolutely present. The fullness we experience comes not from little solid kernels filling every bit of space, but from the way atoms keep one another at bay. When objects meet, it is their electron structures, and the rules governing those electrons that resist further overlap. Matter feels full because it is difficult to compress one atomic arrangement into another beyond certain limits. The world is less like a sack of pebbles and more like a crowded dance floor, where everyone has very firm opinions about personal space. Very small personal space, admittedly, but fiercely defended. There is a quiet elegance in that. The world appears solid because of relations, not because of miniature solidity copied downward without end. Solidity is the large-scale result of microscopic arrangement and interaction. Once you see that, the phrase mostly empty becomes less threatening. It no longer sounds as though the world is somehow fake or insubstantial. Quite the opposite. It suggests that the familiar world depends on deeper and more subtle kinds of organisation than our senses reveal. And it's not only matter at rest that shows this. Think about the difference between materials. Some compress more than others. Some bend. Some shatter. Some conduct electricity. Some do not. If matter were nothing but little hard pellets jammed together, it would be difficult to explain the extraordinary variety of material behaviour. But once atoms are understood as structures with a dense nucleus and a complex outer region, a great deal falls into place. Materials differ because atoms differ and because the ways atoms connect differ. the spaces within atoms, the arrangements among atoms, the allowed states of electrons, all of this shapes the texture of the visible world. It is tempting at this point to ask whether anything is really there between the nucleus and wherever we say the electrons are. And that question is fair, but it is also dangerous because it smuggles in everyday assumptions about particles having neat little locations all the time. In the ordinary world, an object is either here or there. A cup is on the table or in the sink. It is not a cloud of possibilities awaiting gentle philosophical clarification. But electrons force us to think differently. Their presence is not best described as a tiny dot moving along a tiny track. Instead, we are led toward a quantum description in which location becomes a matter of probabilities, distributions and allowed patterns. That is why the atom feels empty to common sense but full to physics. Common sense wants little objects in little places. Physics gives us something subtler. Before we move fully into that subtlety, it is worth noticing how often language tries to pull us back towards solid pictures. We say the electron is around the nucleus. We say it occupies a region. We say it belongs to a shell. These are useful phrases, but all of them are approximations. They help the mind get started. They are not the final story. In truth, the atom teaches a broader lesson that appears again and again in modern physics. Reality at small scales does not always resemble reduced versions of ordinary things. A small chair is still chair-like. A small spoon is still spoon-like. A small atom is not matter behaving in a simply smaller version of ordinary experience. It is matter under different descriptive rules entirely. There is also something unexpectedly reassuring about the atom being mostly empty. It reminds us that nature does not build by cramming. It builds by order. Stability does not require fullness in the crude sense. It requires a lawful arrangement that can endure. A bridge is not strong because every inch of it is solid steel from one end to the other. It is strong because its structure distributes forces in the right way. Matter too has structure. The atom is stable not because it is packed like a cannonball, but because its components occupy allowed states and interact according to consistent rules. The world holds together because nature is organized, not because it is stuffed. And yet one should not overdo the emptiness either. People sometimes hear that atoms are mostly empty and leap immediately to a sort of cosmic disillusionment. Nothing is real, they say. Matter is an illusion. We are ghosts leaning on ghosts. This is an understandable overreaction and a slightly theatrical one. The world remains real enough to bruise your shin and support your bed. The emptiness inside atoms does not make matter unreal. It makes matter sophisticated. There is a difference. The table is not an illusion because its atoms are structured in an unfamiliar way. The table is a triumph of those structures. Perhaps the best way to hold the idea is this. The atom is spacious in terms of dense matter, but not vacant in terms of physical significance. It is mostly open if you're imagining little hard pieces filling volume. It is crowded with rules if you're asking what can happen there. It is almost hollow by one picture and highly organized by another. That is why the phrase mostly empty, strangely full fits so well. The apparent emptiness is real in one sense. The hidden fullness is real in another. Even the nucleus at the center contributes to this strange feeling. It is tiny, yes, but it contains almost all the mass of the atom. Protons and neutrons are gathered there in a compact core, and their presence determines the identity of the element itself. Change the number of protons and you do not merely alter the atom slightly. You get a different element entirely. Hydrogen is not helium. Carbon is not oxygen. Gold does not become gold by believing in itself very hard. The nucleus fixes the elemental identity. And yet, despite this central importance, the nucleus does not determine the atom's size in the everyday sense. That belongs largely to the electron structure surrounding it. So the atom has a center that defines what it is, and an outer region that defines how far it reaches into the world. Already one can feel the old intuition loosening. This also explains why the history of atomic physics kept unfolding in layers. First, the atom seemed indivisible. Then it had internal parts. Then its mass was found to be concentrated in a tiny centre. Then its outer region became a quantum puzzle. Then the nucleus itself turned out to contain particles with deeper structure. Nature has a habit of taking every simple picture and making it provisional. The atom was supposed to be the final brick, it became a doorway instead. And perhaps that is the gentlest way to leave this part of the journey. If the world that looks solid is built from atoms, and atoms are mostly not dense all the way through, then the real question is no longer how anything can be empty. The real question is what exactly fills the atom with consequence? What gives that outer region its structure? What does it mean to say electrons are there if there is no tiny orbiting bead to point at? How can something spread out in possibility still give rise to the hard edge of the world? The closer we get, the less useful our old pictures become, and the next thing waiting for us inside the atom is the most slippery and important part of all, where electrons actually are. The moment we start asking where electrons actually are, the comfortable pictures begin to fail us. This is usually the point in the story where people reach for the old classroom image of the atom and try to hold on to it a little longer. A small central nucleus sits in the middle, and electrons go around it like planets around the sun. It is a tidy image. It has movement, balance, and a kind of mechanical dignity. One can sketch it in a notebook in a matter of seconds and feel that something important has been captured. And for a first introduction, something important has been captured. There is a central nucleus. Electrons are not in the nucleus most of the time. The atom has structure. All of that is useful. But the deeper you go, the less that picture survives. The problem is not that electrons do nothing. The problem is that what they do is not well described by tiny particles following neat little tracks in the way planets follow orbits. A planet can, at least in principle, be thought of as having a definite position and a definite path. Even if the motion is complicated, the basic idea is familiar. At any given moment, the planet is somewhere specific, travelling in some direction, and its future motion can be worked out from the forces acting on it. That kind of picture belongs to the ordinary world, where large objects move through space in smooth ways that our intuition can follow. Electrons do not play by those same rules. This is where atoms stop being merely small and start being genuinely different. An electron is not just a reduced version of a marble or a grain of dust. It belongs to quantum physics, and quantum physics asks us to replace the idea of a precise little object moving along a visible path with something more subtle. When physicists describe an electron in an atom, they do not begin by drawing a tiny line around the nucleus and saying, "There it goes." They begin with a mathematical description that tells them where the electron is likely to be found if they look. That is a very different kind of statement. It is not a map of a route. It is a map of likelihood. So where is the electron? The honest answer is that before a measurement, the best description is not a single exact place like this point here and no other. Instead, the electron is described by a spread of possibilities. There are regions where it is more likely to be found and regions where it is less likely to be found. These patterns are not random scribbles. They are structured, lawful, and specific to the atom and the energy of the electron. But they are not little roads. They are not loops. They are not the kind of thing you could trace with a pencil and say, "This is the path the electron follows each evening after supper." That can feel frustrating at first, because the mind wants a picture. It wants to ask, yes, but where is it really? And this is where the old instincts have to be handled gently. In everyday life, to say something exists but does not have a simple, sharply defined path sounds like evasion. It sounds as though the science has merely become shy. But that is not what is happening. The quantum description works. It predicts the structure of atoms, the light atoms absorb and emit, the way elements behave, the stability of matter itself. The strangeness is not a sign of weakness in the theory. It is a sign that the world at this scale is not built to satisfy our ordinary habits of thought. One reason the planetary model fails is that electrons are not only particle-like in the way we usually imagine matter, they also have wave-like behaviour. That does not mean an electron is secretly a tiny ocean swell or a ripple on a pond wearing a clever disguise. It means that the best description of its behavior includes features we associate with waves, such as interference and standing patterns. Inside an atom, the allowed electron states are better understood as standing wave patterns around the nucleus than as miniature bodies running laps, and that changes everything. Think for a moment about the difference between a path and a pattern. A path belongs to an object that goes from one place to another. A pattern belongs to something spread out across a region in an organized way. If you pluck a string, the vibration of the string can settle into certain stable modes. There are places where the motion is larger, and places where it is smaller. There is structure. There are allowed forms. The electron in an atom is not literally a vibrating string, but the analogy helps with one crucial idea. Nature allows certain stable electron patterns around the nucleus, and not others. The electron states of the atom come in allowed forms. This is why atoms have discrete energy levels rather than a continuous smear of possibilities. That point matters more than it may first appear to. If electrons were little planets, one might expect them to move through a broad range of possible orbits, with a broad range of possible energies. But atoms do not behave that way. They show clear, structured, specific patterns. They absorb and emit light in sharply defined ways. Each element has its own spectral fingerprint because the electrons in that element can occupy only certain allowed states. Those states are not arbitrary. They come from the quantum rules of the atom. So when we ask where electrons actually are, the answer is already tied to which allowed state they occupy. Different states correspond to different probability patterns around the nucleus. This is where the word orbital enters the story, and it is a word that has caused a great deal of quiet confusion because it sounds so much like orbit. The two words are not the same. An orbit suggests a path, a route, a track followed over time. An orbital is a quantum state, a probability pattern, a region characterized by how likely an electron is to be found there when measured. If one keeps that distinction clear, much of the mystery becomes easier to manage. The electron is not orbiting in an orbital the way a planet orbits the Sun. The orbital is the allowed shape of the electron state. These shapes can be simple or more complex depending on the state. Some are concentrated close to the nucleus. Some extend farther out. Some are rounded in their overall probability distribution. Others have more elaborate structures with distinct regions. Again, these are not routes, they are distributions. If you were somehow able to prepare many identical atoms in the same electron state, and then measure where the electron appears each time, the collection of results would build up the characteristic pattern of the orbital. That is one of the most useful ways to think about it. The orbital is the pattern built from many outcomes, revealing where the electron tends to show up. This is also why drawings of electron clouds became so common in modern explanations. A cloud is not perfect as an image, but it is better than a tiny orbiting bead. The darker or denser regions in such drawings represent higher probability, not actual fog. Nothing is literally cloud-like in the ordinary sense. The image is just trying to tell you that the electron is not pinned to a single narrow path. It is described by a spread of possible locations with some regions more likely than others. The cloud picture lets the mind loosen its grip on the old mechanical model. Even that, however, can be misunderstood. People sometimes hear probability and imagine that the electron really is a little bead somewhere precise, but we just do not know where. That sounds reasonable because it matches everyday uncertainty. If you misplace your keys, the keys are somewhere specific. Your ignorance does not make them fuzzy. The problem is that quantum uncertainty is not simply that kind of ignorance. The theory does not just say we lack information about a hidden exact orbit. It sees the exact classical style picture itself is not the right framework before measurement. The spread of possibilities is part of the physical description. This is one of the hardest shifts to accept because it asks us to stop treating the small world as though it were only the large world viewed through a stronger lens. If you zoom in on a fabric, you still see threads. If you zoom in on a pebble, you still imagine smaller pieces of matter. But when you zoom in on the electron in an atom, you're not rewarded with a tiny classical object obeying tiny classical rules. You're taken into a domain where the best possible description is inherently probabilistic. The electron is not hiding from us out of spite. It is telling us, through the results of every good experiment, that our old picture was never the right one. At this point, a very sensible person might ask whether the electron is at least moving. If it is not on a path, is it doing anything at all? The answer is yes, but again not in a way that translates neatly into ordinary imagery. The electron state in an atom has energy, structure, and dynamical properties, but asking for a little moving dot can still lead you astray. In some atomic states, the probability distribution itself can remain stable over time. The atom does not need the electron to be racing around on a little track in order to be active or real. The quantum state is already a form of physically meaningful structure. This point also solves an old problem that appeared in early attempts to imagine electrons as miniature orbiting charges. In classical physics, a charged particle moving in a curve should radiate energy continuously. If electrons really orbited the nucleus like planets in the old model, they would be expected to lose energy and spiral inward very quickly. Atoms would collapse. Matter would not remain stable in the way it clearly does. The quantum description avoids this disaster because atomic electrons are not merely little charges running around in forbidden classical orbits. They occupy allowed quantum states, and these states can be stable. So where are electrons actually? They are in these allowed quantum states around the nucleus, described by probability distributions rather than definite classical trajectories. That is the core answer, but to really feel what it means, it helps to see how much of chemistry and matter depends on it. The outer electrons of atoms determine how atoms interact with one another. Some states are filled, some partly filled, some available for bonding. The arrangement of electrons in these allowed states explains why one element is chemically eager and another is stubbornly unreactive. It explains why the periodic table has structure rather than being a random inventory. The behavior of electrons is what gives the elements so much of their character. Take a simple case. Some atoms have outer electron arrangements that make them especially stable as they are. They do not strongly seek to gain or lose electrons in ordinary conditions. Others have arrangements that make them more willing to share, gain, or give up electrons in order to reach a more stable pattern. This is the beginning of chemical bonding. Atoms join not because they are sociable in any sentimental sense, but because the quantum arrangement of their electrons allows lower energy and more stable combinations under the right circumstances. Molecules form, materials emerge. All of chemistry begins to unfold from where electrons can be and how they can be arranged. The same story appears in light. When an atom absorbs energy, an electron may move from one allowed state to another. When it drops back to a lower state, light can be emitted. Because the allowed states are discrete, the energies involved are discrete, and so the light has specific characteristic values rather than any arbitrary amount. This is why elements produce distinct spectral lines. The atom is not a vague mush. It is a quantum structure with allowed electron states, and those states leave their signature in light. Now, none of this means the electron is a ghost. It can be detected. It has charge. It has mass. It plays a perfectly real part in physical processes. The challenge is not reality. The challenge is description. When the electron is free in some contexts and bound in atoms in others, the best mathematical language we have gives answers in terms of quantum states and probabilities. The reality is there. It is our ordinary visual habits that must adapt. A helpful way to think about this is to separate what a theory predicts from what a picture suggests. The old orbit picture suggests a tiny solar system, because that is easy to draw and easy to remember. The quantum model predicts actual observations correctly. If the picture and the predictions come into conflict, the picture must go. That is one of the quiet disciplines of physics. Nature is under no obligation to remain picturable in the style we prefer. If the atom insists on being stranger than a tidy diagram, then the diagram must be sacrificed. That said, the human mind still needs footholds, so physicists developed layered ways of speaking. In introductory explanations, one might still hear about shells. That can be useful if it is handled carefully. A shell is not a hard spherical casing around the nucleus. It is more like a family of related allowed electron states at similar general energy scales. Within those families, there are more detailed patterns, and within those patterns there are specific arrangements that follow deep quantum rules. As understanding grows, the picture becomes richer and less mechanical. Those quantum rules are not optional details. They govern how electrons can stack into states and why matter remains stable. Two electrons can share the same orbital only if they differ in an internal property known as spin. This restriction helps build the layered structure of atoms and, from there, the structure of the periodic table. It is one reason atoms occupy space in such a robust way. The electrons cannot all collapse into a single lowest condition without regard for these rules. The small world is highly constrained, and the visible world depends on those constraints. Once you see that, the question of where electrons are begins to feel less like a failure of knowledge and more like a lesson in how knowledge works. We do know where electrons are in the sense that we know how to describe their allowed states, how to calculate their probability distributions, how to predict transitions, bonding, and measurable outcomes. What we do not get is the old comforting little path. The atom refuses to hand us a miniature clockwork model, because the atom is not miniature clockwork, it is quantum structure. And there is something almost practical about this strangeness. The world we live in depends on electrons not behaving like tiny planets. Stable atoms, chemical richness, solid matter, electrical behavior, and the entire architecture of everyday substances all emerge from this quantum arrangement. If electrons really moved in classical orbits around nuclei, ordinary matter would not survive in its familiar form. The very bed you lie on owes its existence to the fact that the old picture is wrong. So when someone asks where the electrons actually are, the calmest honest answer is this. They're in allowed quantum states around the nucleus. Those states tell us the regions where an electron is likely to be found when measured. They do not give us a simple little path. They give us a structured probability pattern, and from those patterns come the size of atoms, the shape of bonding, the behavior of materials, and the light that atoms emit. The electron is not nowhere. It is not everywhere. It is not circling like a tiny planet. It is present in a way that quantum physics describes with extraordinary accuracy and ordinary language only approximates. Once that much is in place, the atom starts to look different again. The outer region is no longer a vague emptiness around a tiny core. It becomes a carefully organized quantum domain, full of allowed states, restrictions, and measurable consequences. The electron story explains how atoms reach into the world, how they bond, how they resist, how they shine. But there is still that tiny center waiting for us, the dense region that holds almost all the mass and decides which element an atom is in the first place. And after spending time in the outer quantum territory, it becomes natural to turn inward and ask what is happening at the center, where protons and neutrons are gathered together. Once the outer region of the atom stops looking like a little solar system and starts looking like a quantum structure, the eye naturally turns inward. There is still that tiny center to account for. The atom may extend through its electron states, but almost all of its mass is gathered somewhere much smaller, somewhere much more compact, somewhere dense enough to determine the identity of the element itself. If the electron story tells us how atoms reach into the world, then the nucleus tells us what sort of atom we're dealing with in the first place. And at the center of that nucleus are two kinds of particles that sound almost disarmingly plain when you first meet them. Protons and neutrons. Simple names. Solid-sounding names. The sort of names that suggest the matter has finally become sensible. For a little while, that impression holds. The nucleus is made of protons and neutrons. Protons carry positive charge. Neutrons carry no electric charge. Together they make up the dense central core of the atom. That is a perfectly good starting description, and for many purposes it is enough. But like nearly everything else in atomic physics, the closer you look, the more the apparent simplicity begins to unfold into something stranger and more demanding. It helps to begin with what these particles do for the atom as a whole. The proton is the particle that fixes the identity of the element. Change the number of protons in the nucleus, and you do not merely alter the atom a little, you create a different element entirely. A nucleus with 1 proton is hydrogen, with 2 helium, with 6 carbon, with 8 oxygen, with 79 gold. This is one of the cleanest and most important facts in all of atomic physics. The proton count is the atom's elemental name tag. Everything else may vary in interesting ways, but that number is decisive. It tells you where the atom belongs in the periodic table, and, from there, a great deal about how it is likely to behave once electrons are arranged around it. That alone gives the proton an almost administrative authority over matter. It is not especially dramatic in the way it goes about this. It does not flash or announce itself. It simply sits in the nucleus, positive charge intact, quietly determining whether the atom before you belongs to hydrogen or iron or copper or uranium. In a sense, the proton is the reason the periodic table exists as an ordered structure, rather than a random pile of ingredients. The number of protons climbs step by step, and the elements unfold with it. The neutron, by contrast, often seems a little harder to appreciate at first. It carries no electric charge, so it does not announce its presence through the same kind of electromagnetic behavior. It is not the particle that determines which element you have. If you keep the number of protons fixed and change only the number of neutrons, the atom remains the same element, and yet the neutron matters enormously. Without neutrons, most nuclei would not hold together in anything like the way they do. The neutron adds mass, affects stability, and plays a central role in the quiet internal politics of the nucleus. If the proton is part of the atom's identity, the neutron is part of the reason that identity can persist. The first thing to notice is how extraordinarily concentrated the nucleus is. The atom as a whole has a certain size, largely associated with its electron structure, but the nucleus at the centre is tiny by comparison, and yet almost all the mass of the atom is there. The electrons contribute only a very small fraction of the total mass. Nearly all of it comes from protons and neutrons packed into that central region. So if you're asking where the weight of matter really resides, the answer is not in the broad quantum cloud of electron possibilities. It is in the nucleus. The atom extends through its electrons, but it weighs through its nucleus. That creates one of those scale mismatches that physics enjoys so much. The part of the atom that occupies most of its extent is not the part that contains most of its mass. The part that gives the atom its size is not the part that gives it its heft. The centre is tiny, but it is heavy. The outer region is spacious but light. If atoms were cities, the nucleus would be a tiny district containing nearly all the population, the government, the archives, and an unreasonable amount of internal tension, while the rest of the city would be a vast controlled zone governing how the whole place interacts with its neighbours. And tension really is the right word. A nucleus is not just a peaceful little bundle of particles sitting there because they happen to like one another. In fact, if you consider only electric charge, the whole arrangement looks rather problematic. Protons are positively charged. Positive charges repel one another. So if a nucleus contains more than 1 proton, there is an electric push trying to drive those protons apart. That is not a minor detail. It is one of the basic facts of the nucleus. Every proton is feeling the repulsion of the others, and yet the nucleus does not simply fly apart in most atoms. Something stronger, acting over very short distances, holds it together. We will come properly to that force later, because it deserves its own careful treatment, but even here it is impossible not to feel its presence. The nucleus is stable not because repulsion disappears, but because another interaction overpowers it at close range. This is where neutrons become especially important. Neutrons do not add electric repulsion because they are uncharged, but they do participate in the binding of the nucleus. They help hold the whole compact structure together without increasing the electrical hostility among the protons. That makes them extraordinarily useful. Too few neutrons and many nuclei become unstable, because the repulsive effect of the protons is not sufficiently balanced by the binding influence that acts between nucleons, which is the collective name for protons and neutrons. Too many neutrons, however, can also create instability. The nucleus is not just a pile of particles, it is a structured arrangement with delicate constraints, and the balance between protons and neutrons matters. This is one reason isotopes exist. The word sounds technical, but the basic idea is simple. Atoms of the same element always have the same number of protons, but they can have different numbers of neutrons. Those different versions are called isotopes. Carbon, for example, always has 6 protons, because that is what makes it carbon, but it can come with different neutron counts. Some forms are especially stable, others are unstable, and slowly transform over time. The chemistry of isotopes is often very similar, because chemistry depends so much on the electrons and the proton count that shapes their arrangement. But the mass and nuclear behaviour can differ significantly, because the neutrons differ. That means the nucleus adds a second layer of variety to matter. The proton tells you what element you have. The neutron count tells you which isotope of that element you are dealing with. Same element, slightly different nuclear makeup. Same general chemistry, different nuclear properties. Already the centre of the atom is becoming more interesting than a simple dense core. It is not just there to provide mass, it carries information about stability, decay, and identity at once. There is also something quietly humbling in how small the nucleus is compared with the atom. We speak of the centre as though it were some large central chamber, but in truth it is tiny beyond ordinary imagination. And yet within that tiny region, protons and neutrons are packed together with a density so extreme that it no longer resembles any matter we encounter in daily life. The wood of a desk is mostly atoms with broad electron-defined spacing between nuclei. The nucleus itself is compact on a completely different level. Its density is not a mild version of ordinary solidity. It is matter compressed into a regime that belongs to nuclear physics rather than the everyday world. That is why the atom can be mostly open in one sense, while hiding such an intense concentration at its centre. When physicists first uncovered the nucleus, it was a revelation precisely because it contradicted softer, more spread-out pictures of atomic structure. Suddenly the atom had a core, not a vague one, not a distributed pudding of positive charge, but a genuine centre dense enough to deflect incoming particles dramatically when struck in the right way. Once that was known, the question immediately became what this core was made of. Protons were identified. Then it became clear that protons alone could not explain nuclear masses and behaviours. The neutron followed. With that, the nucleus began to look like a compact society of 2 particles, one charged and one neutral, locked together under conditions unlike anything at larger scales. And yet even with protons and neutrons identified, the nucleus does not become easy. It becomes merely legible. A nucleus can be stable for the age of the universe or unstable enough to transform in moments. Some nuclei are small and simple, others are enormous and precarious. In lighter elements, the balance between protons and neutrons can be relatively straightforward. In heavier elements, the balancing act becomes more delicate. The electric repulsion between many protons grows stronger as more protons are packed into the nucleus, and more neutrons are needed to help maintain stability. Even then, there are limits. Beyond a certain point, the nucleus becomes increasingly fragile. It may hold together for a while, but the strain shows. That fragility is what gives rise to radioactive decay, though that story deserves a slower treatment when we come to unstable atoms more directly. For now, it is enough to notice that the nucleus is not guaranteed to last simply because it exists. Some nuclear arrangements are comfortable, in the limited sense available to subatomic matter. Others are restless. They shed particles or energy. They rearrange themselves into more stable forms. The centre of the atom is not always a quiet place. Sometimes it is only temporarily still. This is another reason the neutron is so important. A neutron can help stabilize a nucleus, but it can also be part of an unstable arrangement. In some cases, a neutron may transform into a proton through processes that change the nature of the nucleus. In other cases, extra neutrons may make the nucleus too heavy or too eager to reorganize. Stability is not just a matter of having many neutrons or few, it is a matter of the right balance for a given proton count. Nature is not following a single simple rule here. It is managing a complex set of constraints in which the nucleus must find one of the arrangements that can endure. There is an appealing irony in this. The proton defines the elements so cleanly that one might expect the nucleus to be straightforward, but identity is not the same as stability. Knowing what element you have does not tell you automatically whether its nucleus is calm or strained, common or rare, long-lived or fleeting. The centre of the atom keeps its own records. It is also worth noticing how much of the visible universe depends on the existence of protons and neutrons in just this form. Stars fuse light nuclei into heavier ones. The elements that make planets, rocks, oceans, bones, blood and atmosphere all depend on nuclei with particular proton and neutron arrangements. Carbon exists because a nucleus with 6 protons can be formed and held together. Oxygen exists because a nucleus with 8 protons and the right number of neutrons can remain stable enough to populate the cosmos. Iron, calcium, silicon, nitrogen, phosphorus, all the familiar cast of terrestrial matter depend on nuclear architecture that could easily have been otherwise. Had the underlying nuclear rules differed even modestly, the menu of available elements might have been much poorer, and the chemistry of life with it. Still, one must be careful not to treat protons and neutrons as featureless pebbles just because they sit in the nucleus. They have mass, yes. They occupy the core, yes. They look like the solid, sensible end of the story, yes. But they are not inert little lumps. Even before we ask what lies inside them, we can see that they have properties, interactions, and internal differences that matter greatly. The proton carries positive charge. The neutron does not. Their masses are close but not identical. They participate in nuclear binding. They can be transformed under the right conditions. They obey quantum rules of their own. The nucleus is not a jar of marbles. It is a quantum many-body system, compact and difficult, ruled by forces and constraints that do not resemble ordinary mechanics. That phrase, many-body system, may sound severe, but its meaning is quite manageable. It simply means that once many particles are gathered together and interact strongly, the whole arrangement becomes more complicated than a simple one-particle picture. Each proton and neutron is influenced by the others. The whole nucleus has collective behaviour. There can be structured energy levels within the nucleus, just as there are structured states for electrons in the atom. The centre has its own hidden architecture. Even there, nature resists becoming merely simple. And there is one more point that deserves some quiet attention. When we say protons and neutrons are at the centre, we should not imagine them frozen in place like beads glued inside a toy. The nucleus is not static in that childish mechanical sense. Its particles are bound, yes, but they are part of a quantum object. The centre is dynamic, not in a sloppy, chaotic way, but in the sense that the nucleons are governed by internal motion, energy, and allowed states of their own. Nothing about the atom, once properly viewed, is ever truly a little still model. Even the stillness of matter is made from activity. That is perhaps the recurring lesson of the whole subject. Every time the world appears calm, physics finds organised motion underneath. Every time a thing looks solid, there are interactions. Every time a structure seems basic, there is another layer. The nucleus looked like the solid answer to the atom. Then the nucleus turned out to contain protons and neutrons. That felt satisfying for a while. But once science had learned to look more closely, even those particles stopped being final. And that, in a way, is the most perfect trapdoor of all. Because protons and neutrons seem like the end of the descent. They sit in the densest part of the atom. They account for its mass. They define its identity and stability. They sound elemental, foundational, almost comfortably final. Yet they are not fundamental in the deepest sense either. They too have structure. They too are made of smaller constituents, held together by deeper rules, and once you realize that the nucleus is built from particles that are themselves not simple, the story opens again and leads us downward into the next hidden layer, where protons and neutrons give way to something smaller still. If protons and neutrons were the end of the story, physics would already have done very well for itself. We would have a nucleus made from two kinds of particles, one positively charged and one neutral, and that would already explain a remarkable amount about atoms, elements, isotopes, and the stability or instability of matter. It would be a perfectly respectable stopping point. Many good science lessons stop there, many very decent diagrams stop there, and for a while, science itself stopped there too, not because anyone was fully satisfied, but because nature had not yet made the next layer easy to see. But as the methods of physics became more powerful, and the questions became more persistent, protons and neutrons began to lose that feeling of finality. They were not indivisible after all. They were not tiny featureless pebbles at the centre of the atom. They had structure, they had parts. And once again, the thing that had seemed like the answer turned out to be another doorway. That next doorway leads into the world of quarks, which are among the strangest ingredients modern physics has ever learned to take seriously. The first difficulty is that quarks do not behave like ordinary objects in any familiar sense. They do not sit around waiting to be picked up one by one like grains of sand. They do not wander freely through the world where we can isolate them, line them up, and admire their neat individuality. In fact, one of the most remarkable facts about quarks is that they are never seen alone under ordinary conditions. They live inside larger particles such as protons and neutrons, bound so tightly that pulling them apart does not produce a lonely free quark drifting out into the open. It produces something else altogether. Nature, for reasons buried deep in the rules of the strong interaction, has arranged things so that quarks stay confined. Now that word confined can sound a little theatrical, as though the quarks are imprisoned somewhere in a microscopic dungeon, rattling their tiny bars and composing complaints about working conditions. But the deeper point is less dramatic and more surprising. Quarks are not just hard to separate because they're sticky in the everyday sense. They are governed by a force that behaves differently from the ones our ordinary intuition is used to. With gravity and with electric forces, distance weakens the interaction. The farther apart things are, the less they influence one another. With quarks, the situation is more troublesome. The farther you try to pull certain quarks apart, the more energy the system stores, until the effort of separating them can create new particles instead. It is as though the universe looks at your attempt to isolate a quark and says no, but here is a fresh batch of bound particles for your trouble. Before we get to how that works, it helps to understand why physicists started believing in quarks at all. This was not an act of poetic imagination, though if it had been, one would have had to admit it was unusually successful. It began as a way of making sense of an increasing collection of particles being discovered in experiments. Once scientists learned how to probe matter at higher energies, they began to find a growing zoo of subatomic particles. There were protons and neutrons, yes, but also many other short-lived particles with different masses, charges, and behaviours. The list became crowded enough to suggest that perhaps these were not all fundamental. Perhaps there was some deeper pattern hiding underneath, some smaller set of ingredients from which many of these particles could be built. That suspicion turned out to be exactly right. Quarks were proposed as the smaller building blocks behind several larger particles. In the case of protons and neutrons, the pattern is especially important. A proton is made from 3 quarks. A neutron is also made from 3 quarks. The particular combination differs, and that difference explains why the proton carries positive charge while the neutron does not. Already, this is a rather striking thing to say. The particles that make up almost all the mass of ordinary atoms are themselves made from even smaller entities, and the charge of the larger particle depends on the combination of charges carried by the quarks inside. This is where the naming conventions of particle physics become both useful and a little absurd. Quarks come in different types, which physicists call flavors. That word sounds as though someone briefly mistook fundamental physics for a dessert menu, but the meaning is straightforward. It just refers to the different categories of quark. The most important ones for ordinary matter are called up and down. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. The electric charges of these quarks are not the same as the charge of an electron or proton in simple whole units. Instead, they come in fractional amounts, and when combined in the right way, they produce the total charge of the proton or neutron. Now, if all of this is sounding slightly less intuitive than even the electron story, that is because it is. Electrons may have forced us to let go of little planetary orbits, but at least an electron can exist as an individual particle in the world. Quarks are even less cooperative. We do not encounter them directly in isolation. We infer them through theory and through the products of high-energy experiments, where the inner structure of protons and neutrons reveals itself under violent enough conditions. The evidence is strong, precise, and widely confirmed, but the visual imagination once again finds itself lagging behind. One cannot simply picture a proton as 3 tiny marbles sitting calmly inside it, like peas in a pod. The reality is more dynamic, more energetic, and less tidy than that. A proton is not a little container with 3 quarks rattling about in the ordinary mechanical sense. It is a quantum object, and its inside is active. The quarks are there, but so are other contributions arising from the fields and particles involved in the strong interaction. Energy is present. Gluons are present, which are the particles that carry the strong force between quarks. Temporary quark and antiquark pairs can also appear as part of the restless quantum activity inside. So when we say a proton contains 3 quarks, that is true in the important structural sense, but it should not tempt us into imagining a quiet interior with only 3 objects sitting politely in fixed positions. The proton is more like a dynamic bound state, a ceaselessly active system whose identity comes from its quark content and the powerful force that holds that content together. This is one of the places where modern physics becomes genuinely difficult to picture without sliding into oversimplification. The proton has mass, charge, spin, and a stable role in matter, but its interior is not calm. It is not a miniature version of a solar system or a box of ball bearings. It is a domain of intense interaction, with quarks exchanging gluons and with quantum fluctuations contributing to the overall structure. The neutron is no simpler. It too is a bound state of quarks and gluons, differing from the proton in its particular quark makeup and therefore in its overall charge and behaviour. There is something almost mischievous in the way nature keeps doing this. The atom looked simple from afar and became complicated up close. The nucleus looked compact and decisive, then split into protons and neutrons. Protons and neutrons looked like basic particles, then opened into quarks. At every step, the thing that seemed final turned out not to be final at all. One begins to suspect that reality enjoys withholding its last layer purely on principle. Still, quarks are not just smaller pieces in a stack. They bring with them an entirely different set of rules. One of the strangest is the property known as colour charge. This has nothing to do with visual colour. Quarks are not secretly red or blue in any everyday sense. The term is a label, and admittedly a rather cheeky one, for the kind of charge associated with the strong interaction. Just as electric charge governs electromagnetic behaviour, colour charge governs the way quarks interact through the strong force. The language sounds playful, but the physics behind it is severe. Quarks come in a different colour states, and the rules of their combinations help determine how larger particles can be built. This is where protons and neutrons belong to a broader family called hadrons, particles made of quarks and held together by the strong interaction. Protons and neutrons are specifically made from 3 quarks. There are also particles made from a quark paired with an antiquark. The world of high-energy physics contains many such combinations, most of them unstable and short-lived. Ordinary matter, however, relies on the comparatively durable presence of protons and, within nuclei, neutrons. The other members of the family appear in energetic environments or in experiments, then decay away. A curious consequence of this is that the stable world around us depends on particles whose internal life is anything but serene. Your bones, your breath, the steel in a bridge, the calcium in teeth, the oxygen in blood, the silicon in stone. All of it is built from atoms whose nuclei contain protons and neutrons, and those protons and neutrons are themselves active assemblies of quarks bound by gluons. The ordinary world is resting on a deeper level of confinement and interaction that almost never announces itself in public. A person can go through an entire life using forks, opening doors, boiling water, and paying taxes without ever needing to think about quarks. And yet quarks are there all the same, helping make protons and neutrons into the durable components of nuclei. It is also worth pausing over the fact that most of the mass of the proton and neutron does not come simply from adding up the tiny masses of the quarks inside. This is one of the most surprising features of the story. The quarks contribute, certainly, but a great deal of the mass arises from the energy of the strong interaction itself, from the motion and binding inside the particle. That means the mass of ordinary matter is, in a very real sense, tied to internal energy and confinement. The weight of the visible world is not just a straightforward pile of little masses stacked together. It comes significantly from the energetic structure of the particles at the heart of the nucleus. That idea can feel slippery the first time it's encountered, because our everyday intuition wants mass to mean stuff, and only stuff. But modern physics asks for a broader view. Energy contributes to inertia and mass-like effects. Bound systems can weigh more because of the energy involved in their internal structure. So the proton is not merely three quarks sitting there and adding themselves up like coins on a table. It is a richly interactive system, and that interaction matters for its mass. If you were hoping that things would become more concrete as we went smaller, I am afraid the opposite keeps happening. Even the neutron, which sounds so calm and practical, contains this same hidden drama. Inside the neutron are quarks and gluons in restless relation. Outside the nucleus, a free neutron does not last forever. It will decay after a while into other particles. Inside a stable nucleus, however, a neutron can remain for immense stretches of time, so its fate depends on context. Bound in matter, it helps create stability. Isolated, it reveals its own impermanence. There is something almost biographical about that, though one should not lean too hard on the comparison. The neutron is not sensitive. It is simply obedient to the conditions nature gives it. Quarks themselves come in more flavours than the up and down types that dominate ordinary matter. There are heavier varieties as well, with names that have the slightly improvised feel of scientists reaching the edge of dignified terminology and deciding to have a little fun. Strange, charm, top, bottom. These quarks appear in high-energy processes and in short-lived particles, and they deepen the sense that the subatomic world is much richer than everyday matter alone would suggest. The visible world around us is built mostly from the lightest and most durable combinations, but the laws of nature permit a broader cast of characters, many of them fleeting. High-energy experiments become a kind of subatomic natural history, revealing species that do not survive long enough to build tables or trees, but are nonetheless part of the deeper structure of the universe. One reason this matters for our story is that it shows how special ordinary matter is. The matter of daily life is not built from every particle nature allows. It is built from the stable combinations that can persist. Protons survive, electrons survive, neutrons survive inside nuclei when conditions are right. Those ingredients are enough to build atoms, chemistry, planets, weather, and nervous systems. But beneath that practical economy lies a much broader possibility space. A whole hidden population of particles that exist briefly and disappear, leaving traces in detectors and in equations rather than in kitchens and coastlines. And yet, for all the complexity, the key point remains pleasingly direct. Protons and neutrons are made of quarks. Quarks are held together by the strong interaction, carried by gluons. They cannot ordinarily be isolated. Their combinations produce the larger particles that make nuclei, and through nuclei they contribute to the structure of every atom in the visible world. That is the clean backbone of the story, however complicated the details become. There is also a philosophical shift hiding in this descent. At first, matter seems to consist of things. Then the things turn into systems. The atom is a system. The nucleus is a system. The proton is a system. The deeper we go, the less useful it becomes to imagine nature as a stack of tiny hard objects, and the more useful it becomes to think in terms of interacting fields, allowed states, and bound structures. The particle language remains essential, but the particles are not little billiard balls in a cosmic cupboard. They are excitations and combinations and dynamically maintained identities within a framework that is more subtle than common sense ever asked for. Perhaps that is why quarks feel so distant even when they are inside every proton and neutron around us. They belong to a level of description that our senses were never built to encounter. We do not see them. We do not feel them directly. We do not notice their confinement in ordinary experience. But when physics pushes hard enough against matter, when experiments reach into the interior of the proton, when theory and measurement align, quarks emerge as unavoidable. They are not a decorative extra. They are part of the actual machinery inside the particles that build nuclei. This is also the point where the darkness in the title begins to make practical sense. Quarks live hidden from direct isolation. They do their work inside larger particles, behind the calm surfaces of matter. They are not dark because they are mystical. They are dark because they remain confined, because they inhabit a domain that ordinary experience never illuminates, because the world we touch every day keeps its deepest workings tucked out of sight. The atom already taught us that reality can be mostly hidden while producing obvious effects. Quarks simply take that lesson one level deeper. And once quarks are in view, the next question is not hard to guess. If protons and neutrons are held together by quarks, and quarks are held together by gluons, then what exactly is this force doing all the way through the atom? What keeps quarks bound inside protons and neutrons? What keeps protons and neutrons bound inside nuclei despite their electrical repulsion? What lets the atom as a whole hold together without flying apart into a cloud of disagreements? At every level of the descent, structure has depended on force, and now that we have gone smaller still, the need to understand those forces becomes impossible to ignore. By the time we reach this point, the atom has stopped looking like a simple object and started looking more like a layered agreement. Electrons do not simply drift away. The nucleus does not simply burst apart. Quarks do not simply escape from protons and neutrons and wander off into the world. At every level, something is holding, guiding, restricting, allowing, refusing, and that is really what forces are in this story. They are not just pushes and pulls in the childlike sense. They are the rules by which matter can keep its shape, keep its identity, keep its stubborn presence in the universe. Without them, the atom would not be an atom for longer than a moment, if it could exist at all. Matter would lose its structure before it ever had a chance to become stone or blood or ocean or breath. It is easy to say that everything is held together by forces, but that sentence can sound flatter than it deserves. In the ordinary world, a force sounds like something simple. You push a door. Gravity pulls a falling cup downward with its usual lack of tact. A chair pushes upward when you sit on it. These are familiar experiences, but inside the atom, the word force means something deeper. It means the fundamental interactions that govern what particles do, how close they may come, how tightly they may bind, how they exchange energy, and whether some structures can remain stable while others cannot. The atom is held together because several different interactions are each doing their part, each on its own scale, each with its own range and character. The most obvious one in the atom, at least once electrons come into view, is the electromagnetic interaction. This is the force associated with electric charge, and it shapes almost everything about how atoms interact with one another and how electrons are bound to nuclei. A proton carries positive charge. An electron carries negative charge. opposite charges attract. This simple fact is one of the great architects of the visible world. It is why electrons can remain bound in allowed states around the nucleus. It is why atoms exist as structured entities rather than as isolated, naked nuclei surrounded by nothing. It is why chemistry can happen at all. If the electromagnetic interaction were not there, the nucleus would sit alone, stripped of electrons, and all the rich variety of atomic behavior would vanish. There would be no chemical bonds in the ordinary sense, no molecules, no solids with familiar textures, no gases with ordinary properties, no water, no wood, no skin, no paper, no breathing life to wonder where all the matter went. The attraction between the positive nucleus and the negative electrons is the beginning of atomic structure as we usually mean it. And yet even here the story is not as simple as one charge pulling directly on another in the old mechanical way. Electrons do not fall into the nucleus like tiny pebbles into a well. They occupy allowed quantum states. Their behavior is structured. The electromagnetic force sets the stage, but quantum rules determine the possible arrangements. So when we say the nucleus holds the electrons through electrical attraction, that is true, but it is not the whole truth. The attraction is real, the binding is real, and the allowed forms of that binding are governed by quantum mechanics. The atom is not built from force alone. It is built from force under law. That is part of what makes the atom so satisfying to think about. Nothing is ever just one thing. The electrons are held by electromagnetic attraction, yes, but they are held in precise allowed states rather than in a continuous blur of arbitrary possibilities. Those states determine the size of the atom, the distribution of its electrons, the energies it can absorb and emit, and the way it presents itself to neighbouring atoms. The force pulls, the quantum rules shape. Between them, matter acquires form. Still, the electromagnetic interaction is not only a force of attraction, it is also a force of refusal. Electrons repel other electrons because, like charges repel, protons repel other protons for the same reason. This is why the electromagnetic interaction does not merely bind matter, it also gives matter its resistance and its surface. When two objects seem to touch, what is really happening is that the charge structures of their atoms are interacting and refusing deeper overlap. The world feels solid not because matter is packed with tiny hard beads, but because the electromagnetic behavior of atomic outer regions prevents easy penetration. Your hand stops at the table because the charges and quantum states in the atoms of your skin and the atoms of the wood are not interested in sharing the same space in the same way. So already one force is doing several jobs. It binds electrons to nuclei. It governs much of chemistry. It shapes the interactions between atoms. It helps produce the solidity of matter. It makes possible light itself in the atomic sense, because electron shifting between allowed states absorb and emit electromagnetic radiation. Even before we go deeper, the electromagnetic interaction has already earned a rather large share of the credit for the world, you know. But once we look inward at the nucleus, a problem appears immediately. Protons are all positively charged. Positive charges repel one another. So why does the nucleus not simply tear itself apart? In a hydrogen nucleus, which is just a single proton, there is no issue. But the moment you place two protons close together, the electrical repulsion is real and strong. Add more protons and the problem grows worse. A larger nucleus ought to be under enormous internal pressure to fly apart, and yet many nuclei remain stable for billions of years. So something must be acting there. Something powerful enough to overcome the electric repulsion at very short distances. This is where the strong interaction enters. The strong interaction is one of the deepest and most consequential forces in nature. At the level of quarks, it is the force that binds quarks together inside protons and neutrons. Without it, quarks would not form those particles in the first place. There would be no protons, no neutrons, no nuclei. The strong interaction is carried by particles called gluons, and the name, for once, is unusually helpful. They really do bind quarks together, though not like glue in the soft and sticky everyday atoms. They are part of an intense quantum interaction that keeps quarks confined within larger particles. This is already a remarkable role, but the strong interaction does something else as well, or rather a closely related leftover effect of it does. Protons and neutrons inside nuclei are themselves bound together by what is often called the residual strong force. The deepest strong interaction is operating among quarks inside each nucleon, but some of its influence spills outward in a way that allows whole protons and neutrons to attract one another strongly at very short range. This attraction is powerful enough to overcome the electromagnetic repulsion between protons, provided the nucleons are close enough together. That is what makes the nucleus possible. This is one of those facts that becomes more impressive the longer you sit with it. The protons in a nucleus are each trying to repel one another electrically, and yet they remain bound because another force acts more strongly at those tiny distances. The nucleus is therefore not a quiet lump, but a victory of one interaction over another in the correct regime. Stability in the nucleus is not the absence of conflict. It is the result of conflict being managed by stronger rules. The neutron plays a particularly elegant part in this arrangement. Because it carries no electric charge, it does not add to the electromagnetic repulsion inside the nucleus. But it still participates in the residual strong binding between nucleons. That means neutrons can help glue the nucleus together, in the broad, everyday sense of the word, without increasing the electrical stress among the protons. This is why neutron count matters so much for nuclear stability. A nucleus needs enough strong binding to remain intact, but too much imbalance in either direction can create instability. The proton count determines the element. The neutron count helps determine whether that element in that particular form can hold itself together. If the strong interaction were only a little weaker, the universe would be a much poorer place. Protons and neutrons might not form as they do. Nuclei beyond the simplest would struggle to exist. The periodic table would collapse into a sad little pamphlet. Chemistry would lose much of its richness before it even began. The existence of carbon, oxygen, nitrogen, calcium, iron, and all the rest depends on nuclear binding working as it does. The stars that forge the elements rely on these nuclear rules. Every heavier atom in your body is an inheritance from a universe in which the strong interaction was up to the job. Yet the strong interaction is peculiar. At the quark level, it has the strange property that quarks cannot be isolated under ordinary conditions. At the nuclear level, its residual effect acts over a very short range. That is why nuclei can exist as compact objects, but the whole world is not one giant universal nucleus. The strong binding between nucleons is powerful, but it does not reach far enough in the same way to cause all matter everywhere to collapse into one bound lump. Atoms remain separate entities. Molecules remain distinct. Chairs do not merge with carpets in an outbreak of excessive enthusiasm. Nature has arranged the range and strength of the interactions in such a way that structure can form on multiple scales, without everything losing its boundaries. Now, there is another force that plays a less obvious but still crucial role in the atomic story, and that is the weak interaction. The name unfortunately makes it sound unimportant, like the shy cousin at a family gathering who contributes nothing but polite nods. In fact, the weak interaction is essential to several of the most profound processes in nature. It is responsible for certain kinds of particle transformation, including the kinds of nuclear decay that change one type of particle into another. A neutron, under the right conditions, can transform into a proton through a weak process. This matters enormously in radioactive decay, in the behavior of free neutrons, and even in the fusion reactions inside stars. The weak interaction does not usually hold structures together in the same obvious binding sense as the electromagnetic or strong interactions. It is more often a force of change than a force of steady support. But that makes it no less important. The universe needs not only stable arrangements but also ways for unstable ones to transform. Radioactive nuclei decay because the weak interaction allows certain particle level changes. Elements can shift from one form to another. Energy can be released. New nuclei can emerge. In the Sun and other stars, weak processes help convert hydrogen into helium in the chain of events that ultimately powers the light and warmth reaching planets. So while the weak interaction may not be the force that lets the atom sit there looking composed, it is part of the reason atoms can evolve, stars can shine, and the inventory of the cosmos can change over time. There is something very elegant in that division of labour. The electromagnetic interaction binds electrons and governs much of the visible behaviour of atoms and light. The strong interaction binds quarks into nucleons and nucleons into nuclei. The weak interaction permits transformation within the nuclear and particle world. Each force has its own character, each speaks its own dialect of nature, and from their combined effects comes the architecture of matter. One might wonder about gravity at this point, and that is fair, because gravity is the force most familiar to daily life. It holds you to the Earth, it shapes planets, stars, galaxies, and the large-scale structure of the universe. But inside the atom, gravity is almost comically irrelevant compared with the other interactions. The gravitational attraction between subatomic particles is so extraordinarily weak at those scales that it contributes essentially nothing to atomic structure. This is one of the oddest facts in all of physics. Gravity rules the large-scale universe, but at the scale of the atom it steps aside almost entirely, leaving the stage to the other three. That mismatch tells us something important about nature. The same universe is governed by different dominant rules at different scales. To understand a falling apple, gravity matters. To understand a glowing atom, electromagnetism matters. To understand why a nucleus holds together, the strong interaction matters. To understand why some nuclei decay and why stars can transmute elements, the weak interaction matters. Physics is not a single story repeated identically at every level. It is a layered account in which different interactions take the lead depending on the regime, and yet even though we can separate these forces conceptually, the atom experiences them together. The atom is not a classroom chart with tidy columns. It is a real quantum system in which these influences coexist. The electrons are bound electromagnetically. The nucleus is bound by the residual strong interaction. The quarks inside the nucleons are bound by the deeper strong interaction. The weak interaction remains available for certain transformations. The whole result is matter that can endure, interact, emit light, undergo chemistry, and sometimes decay. One of the most beautiful features of this arrangement is that the forces do not merely hold things in place, they create possibilities. Because electrons are bound but not frozen, atoms can absorb and emit energy. Because nuclei are strongly bound but not universally stable, some isotopes can decay and release energy. Because quarks are confined, protons can remain stable for immense spans of time. Because the electromagnetic interaction extends beyond a single atom, atoms can bond into molecules and molecules into materials. The forces are not just a set of microscopic restraints. They are the reason the universe has behaviour. That is why the atom is not dead architecture. It is active structure. The forces holding everything together also govern how energy moves through matter. They determine when an atom may be excited, when a nucleus may change, when particles may transform, when light may be taken in or released. The stillness of matter is not the stillness of a statue. It is the stillness of a system whose internal rules are working perfectly well all the time. Perhaps the best way to understand this is to remember that every ordinary object is already a successful compromise between these interactions. A piece of iron remains iron because atomic electrons occupy allowed states around atomic nuclei, because those nuclei are stable enough to persist, because the quarks inside their nucleons remain bound, because the electromagnetic interactions between the atoms create the material properties of the metal, and because the weak interaction has not driven those nuclei into some other form. The calmness of the object is an achievement, not a default, and because it is an achievement, it can be disturbed in interesting ways. Supply energy to an atom and the electrons may shift to higher allowed states. Disturb a nucleus, and it may react, decay, or rearrange. Force particles together under the right conditions and new structures may form. The forces define not only what matter is, but how matter responds. They draw the lines between the stable and the unstable, the allowed and the forbidden, the long-lived and the fleeting. This is where the story begins to lean naturally toward light. Once electrons are bound electromagnetically in specific quantum states, a great possibility opens. Atoms can take in energy. They can release energy. They can jump between allowed configurations, and when they do not merely change silently, they exchange energy with the electromagnetic field itself. They drink light, in a sense, and they spill light back out. The same interaction that binds electrons to the atom also gives the atom one of its most delicate and beautiful habits, the ability to shine in exact and characteristic ways when its internal arrangements change. Once electrons are bound to atoms in those allowed quantum states, the atom acquires one of its most remarkable habits. It can take in light, and it can give light back. Not in a vague decorative sense, not as though the atom occasionally enjoys a quiet glow for aesthetic reasons, but in a very exact and rule-governed way. The atom can absorb energy from light when the amount is just right, to move an electron from one allowed state to another, and when that electron later returns to a lower state, the atom can emit light again. That is what I mean by atoms drinking and spilling light. They do not absorb any amount they please, and they do not emit in a smooth continuous wash, unless vast numbers of them are acting together in complicated ways. They take in specific amounts, release specific amounts, and leave signatures in light that can be read almost like a language. This is one of the great turning points in understanding matter because it reveals that atoms are not mute. They speak through light. Every element has its own pattern of allowed electron states, and because of that, every element has its own characteristic way of interacting with light. If you heat a gas, or pass electricity through it, or shine light through it under the right conditions, the atoms do not respond with random colours or arbitrary brightness. They respond according to their internal structure. They absorb certain kinds of light and emit certain kinds of light. That means the hidden architecture of the atom, which is otherwise too small to see, announces itself in the visible world through glowing lines, missing colours, and precise spectral patterns. The reason this happens is wonderfully strict. An electron in an atom cannot simply occupy any energy it likes. It can only exist in specific allowed states. If the atom is given energy in just the right amount, an electron may move from a lower allowed state to a higher one. This is often called excitation, which makes the atom sound more enthusiastic than it really is, but the word is accurate enough. The atom has absorbed energy. The electron is now in a higher state than before, but that condition does not always last. In many cases, the electron will later return to a lower state, and when it does, the energy difference must go somewhere. Often it leaves as light. That light is not arbitrary. It carries exactly the amount of energy corresponding to the difference between the two states. Because the allowed states are discrete, the emitted light comes in specific amounts rather than in a continuous blur. This is why atoms do not glow with just any colour they fancy. They glow according to their inner structure. Hydrogen has its own pattern, sodium has its own, neon has its own, mercury has its own. Every element carries a sort of optical fingerprint, and once science learned how to read those fingerprints, the universe became much more talkative. There is something deeply satisfying about this. The atom is too small to inspect directly in the everyday sense, but it cannot hide its internal rules once light becomes involved. Heat a sample of a substance and examine the light it emits. Pass electricity through a gas and study the glow. Spread that light out into its component colours, and what appears is not a smooth rainbow, but a set of distinct lines at particular places. Those lines are the marks of transitions between allowed electron states. They are evidence that atoms are quantized systems. They are evidence that electrons occupy specific structured states. In other words, light became one of the first reliable ways the atom confessed what it was doing inside. Before this was understood, light itself was already mysterious enough. People knew that materials glowed when heated, that flames had colours, that some chemicals produced striking hues, that stars shone with different shades and intensities. But once atomic physics and spectroscopy developed together, it became possible to go much further. Light was not just illumination anymore, it was evidence. It was a report from inside the atom. The colour of a glowing gas was not merely decorative, it was diagnostic. It told you what element was present and what its electrons were allowed to do. That is why a sodium street lamp has its characteristic yellow glow, and why neon signs do not all look the same once different gases are involved, and why astronomers can tell what stars are made of even when those stars are unimaginably far away. The atoms do the talking through light, and the patterns are so exact that they can be recognised across enormous distances. A star can be too remote to visit, far too hot to touch, and indifferent to our personal curiosity, but its light still carries the imprint of the atoms inside it. Spread that starlight into a spectrum and suddenly the star is giving testimony. Hydrogen is here, helium is here, sodium is here, iron is here. The hidden electron structure of atoms becomes a way of reading the composition of the cosmos. It is hard to overstate what a triumph that was. Imagine discovering that the faint light from a distant star contains enough information to tell you which elements are burning or glowing there. Imagine realizing that matter on Earth and matter in the heavens obey the same atomic rules. The same patterns seen in a laboratory flame appear in sunlight or starlight. This was not just a technical achievement. It was a profound statement about the unity of nature. The atoms in your blood and the atoms in a distant star are not playing by different local customs. They are following the same quantum rules, and light reveals that. Still, the basic mechanism inside the atom remains pleasantly clear once the allowed states are accepted. An electron begins in one state. The atom receives energy. If the incoming amount matches the gap to a higher allowed state, the electron can move upward. If not, then the light may pass by without being absorbed in that way. This is one of the reasons atoms are so selective. They do not drink just any light. They respond to what their internal structure permits. That selectiveness is what creates absorption lines in spectra. Light from a bright source passes through a cooler gas. The gas atoms absorb only certain specific colours corresponding to allowed transitions. Those colours go missing from the transmitted light, and what remains carries dark lines where those colours were removed. In a sense, the atoms have taken a sip at very particular wavelengths and ignored the rest. Then, after excitation, comes emission. The electron returns to a lower state, often in a cascade of steps rather than one grand leap, and light is released. Again, the emitted colours correspond to the allowed differences between states. That is why emission spectra are not smooth. They are patterned, they are discrete. The atom spills light in exact portions, not in a careless flood. This exactness was one of the great clues that the old classical picture of the atom could not be right. If electrons really moved around the nucleus in any continuous range of ordinary orbits, then the emitted light should also smear across a continuous range more easily. But that is not what was observed. The spectral lines were sharp. The allowed energies were specific. Nature was telling us, in no uncertain terms, that the atom had a built-in ladder rather than a smooth ramp. Electrons could stand on certain steps and not others. Light was the proof. There is a quiet beauty in that ladder image, as long as one remembers it is only an image. The electron does not climb stairs in a tiny pair of boots. It moves between quantum states. But the analogy helps with the important point. There are allowed positions in the energetic sense, and transitions occur between them. The atom is structured. Its interaction with light is therefore structured. Of course, light can enter the story in several ways. A hot object can emit light because thermal motion and collisions within it are energetic enough to excite atoms, or in solids, broader electronic systems. An electric discharge through a gas can excite atoms and make them glow. A passing beam of light can be absorbed if its energy matches an allowed transition. In each case, the atom or material takes in energy and later releases it according to the rules available to its internal structure. The method of excitation may differ, but the quantum bookkeeping remains strict. This is also why materials have colour in the ordinary sense. When white light falls on a substance, some parts of that light may be absorbed more strongly than others, depending on the electronic structure of the atoms and molecules involved. The remaining light is reflected or transmitted, and that is the colour you see. A red object appears red because it is not treating all visible wavelengths equally. It is absorbing some more than others and letting red reach your eyes more effectively. Even everyday colour, then, is tied to the ways electrons can and cannot respond to light. Your shirt, a leaf, a painted wall, the skin of an apple, the evening sky through haze, all of it comes down in part to matter making selective deals with light. The atom's relation to light is not only about colour or glow, it is also about transparency and opacity. Why is glass clear while wood is not? Why does some material let light pass while another stops it? Again, the answer lies in an electronic structure. If the available states of the electrons in the material do not easily absorb certain visible wavelengths, then that light may pass through. If the structure allows strong absorption, then the material may be opaque or strongly coloured. The visual character of the world is inseparable from atomic and electronic behaviour. The room you are in right now looks the way it does because matter and light are negotiating according to quantum rules. There is a lovely irony here. Light is how we usually see the world, yet it is also how the world reveals its hidden microscopic structure. The same thing that lets you see a lamp, a window, a blanket, or the dim outline of a bookshelf is also the thing that carries evidence about electron states, atomic transitions, and the composition of stars. Light is both messenger and message. One should also be careful not to imagine atomic emission as a leisurely act performed with conscious timing. An electron in an excited state is not sitting up there thinking it might stay for one more minute just to enjoy the view. The lifetime of an excited state can vary, but the return to lower states follows quantum probabilities and allowed pathways. Some transitions happen readily, others are less likely. Some excited states last only astonishingly brief intervals. Others can persist a bit longer. Again, the atom is not making choices. It is obeying structure. Yet from that obedience comes a huge range of visible phenomena. This includes fluorescence and phosphorescence, which are among the more charming habits of matter. In some substances, absorbed energy is re-emitted quickly as visible light. In others, the process can involve more complicated pathways, allowing the material to glow for a time even after the original source of excitation is removed. The details belong more to molecular and solid-state physics than to isolated atoms alone, but the principle still traces back to allowed electronic states and transitions. Matter can hold energy briefly and release it later. That soft afterglow on a watch face, the bright response of certain minerals under ultraviolet light, the useful chemistry of modern displays and lamps, all of it rests on the same deeper fact that electrons can be excited and can return. And once the idea is in place, it appears everywhere. Fireworks rely on it. So do neon signs, fluorescent lights, plasma displays, many lasers, and astronomical spectroscopy. Even the warmth of sunlight absorbed by a dark surface begins as electronic and atomic interaction with incoming radiation. The world is not merely lit by atoms, it is constantly exchanging light with them. There is another feature of this exchange that makes atoms especially good storytellers. The transitions are so exact that even slight shifts can matter. Under different conditions, spectral lines can broaden or shift due to motion, collisions, magnetic effects, electric effects, or pressure. That means light does not only tell us what atoms are present, it can also tell us something about what is happening to them. Are they hot? Are they moving toward or away from us? Are they in a strong magnetic field? Are they in a dense environment? Light carries more than identity. It carries circumstance. This is how astronomers infer so much from what seems, at first glance, to be little more than distant points of light. A star is not just a bright spot. Its light can be spread out and read for composition, temperature, motion, and more. The atom, by drinking and spilling light according to exact rules, has made the universe readable at a distance. That may be one of the most generous things matter has ever done for science. At the same time, the story remains intimate. The same principles govern the small events around you. If a lamp is glowing, if a screen is shining, if a candle flame is coloured, if a heated metal bar changes its glow as it warms, atomic and electronic transitions are somewhere in the chain of explanation. The room around you is not only full of matter, it is full of matter in conversation with light. This also reminds us that the atom is never merely static. Even when matter seems still, its electrons can be excited, relaxed, rearranged, or disturbed by incoming radiation. Matter is always available for interaction. Light arrives, electrons respond or refuse. Energy is taken in or not. Emission follows or does not. What looks calm from a distance is actually a constant field of possible exchange. There is a practical strictness to all of this that I find rather soothing. The atom is not improvising. It is not glowing at random. It is not making artistic choices about whether tonight feels more blue than yellow. Its behaviour is lawful. If the electron states are arranged in a certain way, then certain transitions are allowed and others are not. If the incoming light matches an allowed gap, absorption can happen. If the electron falls, emission follows. The rules are stable enough that we can build technologies from them and read the chemistry of stars across space. The world is dependable right down to the fact that its hidden light-making habits are quantized. Even the term quantum, which can sound rather grand in popular speech, is doing modest work here. It just reminds us that the exchanges come in discrete amounts. The atom does not sip a smooth, arbitrary trickle of energy and then dribble it back out in a vague haze. It trades in set differences between allowed states. That is why spectroscopy works. That is why elements have fingerprints. That is why the mystery of atomic structure began to crack open once people learned to analyse light carefully enough. Still, not every atomic event ends with a gentle release of light and a return to business as usual. Some atoms live in arrangements that are not fully stable. Some nuclei, despite all the binding that holds them together, are under strain. They may not merely shift an electron and emit a photon. They may change more deeply. They may transform, shed particles, or release energy from the nucleus itself rather than from the electron structure around it. The calm business of atoms drinking and spilling light leads naturally to a more serious question, because once we've seen how orderly atoms can be, it becomes more striking that not all of them remain content to stay as they are. Some, sooner or later, begin to fall apart. By now, the atom has shown itself to be far less simple than the old pictures ever suggested. It has a tiny, dense nucleus carrying almost all of its mass. It has electrons arranged in allowed quantum states rather than little planetary tracks. It can absorb light and emit it again in exact amounts. It can join with other atoms to build chemistry, materials, bodies, weather, and worlds. And for many atoms, that structure is remarkably durable. They remain what they are for timescales so long that human history hardly registers against them at all. Stone stays stone, oxygen remains oxygen. Carbon continues being the great reliable organizer of life and ash and diamond and soot. Much of matter is patient, but not all of it. Some atoms contain nuclei that are not entirely at ease with themselves. They exist, certainly. They can sit in matter, take part in chemistry, and appear quite ordinary for a time. Yet deep in the nucleus there is a tension that does not fully resolve. The balance among protons and neutrons is not quite right, or the nucleus is too large, or its internal arrangement leaves open a more stable possibility. And so, sooner or later, the atom changes. It does not change because it is struck from outside in the way a glass might shatter when dropped. It changes from within. Its nucleus rearranges or sheds something or transforms one of its particles, and in doing so it becomes a different nuclear state, often a different element or isotope altogether. That process is what we mean when we say an atom falls apart. Now that phrase can be a little misleading if taken too dramatically. It suggests a total collapse, a complete destruction, as though the atom simply gives up and vanishes in despair. Usually it is not like that. The atom does not disappear into nothing. Instead, its nucleus undergoes a change toward a more stable configuration. Something is emitted. Some excess energy is released. A proton may turn effectively into a neutron, or the reverse through weak processes. A compact cluster may leave the nucleus. The identity of the atom may shift. The fall is not always an explosion in the everyday sense. Often it is a transformation, a reorganization, an internal correction. To understand why this happens, it helps to return to the nucleus itself and remember what a precarious structure it really is. A nucleus is made of protons and neutrons packed into a tiny region. The protons are positively charged, and so they repel one another electrically. That repulsion never takes a day off. Every proton in the nucleus feels it. But the nucleus is also held together by the residual strong interaction between nucleons, and that attraction is powerful enough at very short range to bind the nucleus despite the electrical hostility. So nuclear stability is never a simple default. It is a balance. The strong binding must be sufficient. The proton count and neutron count must cooperate. The total arrangement must land in one of the configurations that can endure. Some nuclei achieve this balance beautifully. Others achieve it only provisionally, and some miss it enough that change becomes inevitable. One easy way to see the problem is to imagine what happens as nuclei become larger. A small nucleus with a modest number of protons may be held together quite effectively by the strong interaction. Add more protons, however, and the electrical repulsion among them grows. That does not automatically make the nucleus unstable, because additional neutrons can help increase the binding without increasing the repulsion. But this strategy has limits. As nuclei get very heavy, the balance becomes harder to maintain. The nucleus begins to resemble a crowded arrangement under strain, with the strong interaction holding things together over short ranges, while the cumulative electrical repulsion among many protons keeps pushing outward. Stability becomes more delicate. That is why many of the heaviest nuclei are radioactive. They are simply too burdened by internal tension to remain unchanged forever. Some can last a long time before decaying. Others go quickly, but in each case the underlying logic is similar. The nucleus can lower its energy or reduce its strain by changing into something else. There are several main ways this happens, and each reveals something slightly different about what the nucleus is trying to fix. One of the most familiar is alpha decay. In this process, the nucleus emits a compact cluster made of 2 protons and 2 neutrons. This cluster is essentially a helium nucleus. When a heavy unstable nucleus emits one, it reduces both its proton count and its neutron count, stepping downward toward a different nucleus that may be more stable. This is not a random handful of particles breaking off in a messy way. The emitted cluster is a particularly stable little package, and its departure helps relieve the parent nucleus. There is something almost architectural about that. A very heavy nucleus is not merely exploding from irritation. It is shedding a compact piece of itself in a lawful attempt to move into a more favourable condition. The element changes because the proton count changes. The isotope changes because both proton and neutron counts change. Energy is released in the process, and what remains is often still radioactive, continuing along a chain of decays until a stable nucleus is finally reached. Another important route is beta decay, which is subtler because it involves a change in the identity of a particle inside the nucleus. In one common form, a neutron turns into a proton through a weak interaction process, and an electron and another light particle called an antineutrino are emitted. In another form, a proton can effectively turn into a neutron, involving the emission of a positron and a neutrino, or the capture of an electron from the atomic surroundings. These processes occur when the ratio of protons to neutrons in the nucleus is not favourable. The nucleus is adjusting its internal composition, trying to move toward a better balance. This is a lovely reminder that instability is not always about size alone. A nucleus can be too rich in neutrons or too rich in protons relative to what works best for that element. Beta decay is the nucleus's way of correcting that imbalance. It does not necessarily need to throw off a large chunk of matter. Sometimes it only needs to change the type of one nucleon and let the whole arrangement relax into a more stable pattern. Then there is gamma emission, which is different again. Sometimes a nucleus is left in an excited state after some other process and can release excess energy by emitting very energetic light. In this case, the proton and neutron counts do not change. The nucleus remains the same isotope, but it moves from a higher energy configuration to a lower one. This is somewhat analogous to electrons emitting light when they drop between allowed states, except now the transition belongs to the nucleus rather than the electron cloud around it. The atom is releasing energy from its center rather than from its outer electronic structure. Already one can see that falling apart is not one single event, but a family of related possibilities. The nucleus may eject a compact cluster. It may change one kind of nucleon into another. It may release internal energy as high-energy radiation. The common thread is that the original configuration is not the most stable one available, and nature has a way of finding the lower ledge. The word stability here deserves careful handling, because it does not mean comfort in any human sense. A stable nucleus is not one that enjoys life, feels secure, or has achieved peace of mind after years of patient reflection. It simply means that there is no available process likely to occur that would take it to a lower energy state under ordinary conditions, or that such a process is so unlikely that the nucleus persists for enormous times. An unstable nucleus, by contrast, has a significant chance of changing. That chance may be large or small. Some unstable nuclei decay in fractions of a second. Others survive for thousands, millions, or billions of years. Radioactivity is governed by probabilities, not clocks hidden inside each atom. That point matters a great deal. An unstable atom does not age in the way a living thing ages. It does not slowly wear down particle by particle until the moment arrives. Every nucleus of a given type carries a certain probability of decaying in a given span of time. One atom may decay quickly, another identical one may last much longer. There is no tiny alarm going off inside at a prearranged second. This is one of the most direct places where quantum probability enters the nuclear story. All we can predict with confidence is the statistical behaviour of large numbers of such atoms. This is where the idea of half-life becomes useful. A half-life is the time it takes for half of a large sample of radioactive nuclei to decay on average. It does not mean that each individual nucleus waits exactly that long and then obediently disassembles on schedule. It means that if you begin with a large enough collection, the number that remain undecayed drops by half over each half-life interval. This statistical regularity is one of the most remarkable features of radioactivity. Individual events are unpredictable in timing, yet the overall pattern is astonishingly precise. There is something quietly eerie about that. A single nucleus keeps its own counsel. No one can say which one will go next in a given large sample, yet the crowd behaves lawfully. Nature is uncertain in the individual case, and reliable in the aggregate. That is a deeply quantum kind of behaviour, and it prepares the mind for what comes later when we look more directly at the quantum world underneath matter. But staying with the nucleus for a moment longer, it is worth asking why the release of energy accompanies radioactive decay. The answer is that the final configuration is often more tightly bound, or otherwise lower in energy than the initial one. The difference must emerge somehow, and it does so as emitted particles, radiation, or kinetic energy of the products. The original nucleus was holding more energy in its strained or excited arrangement than the final one needs. Decay is the route by which that excess is released. This is why radioactive substances can be sources of heat and radiation. It is not that they are drawing energy from nowhere. The energy is bound up in the nuclear arrangement itself. When the arrangement changes to something more stable, that stored difference is let out into the world. In a tiny amount of matter, the energies involved can be surprisingly large compared with ordinary chemical processes, because nuclear binding reaches much deeper into the structure of matter than chemistry does. Chemical reactions rearrange electrons and bonds between atoms. Radioactive decay rearranges the nucleus itself. That is a more serious intervention. Still, one must not imagine every radioactive sample as a dramatic menace glowing green in a basement laboratory, while ominous music gathers in the distance. Much radioactivity in nature is modest, persistent, and ordinary. The Earth contains radioactive elements. Rocks contain them. The air carries traces from decay chains. Living things contain small amounts of naturally occurring radioactive isotopes. Even your own body includes a little natural radioactivity. The world is not free of unstable nuclei. It never was. Life emerged and persists in a universe where some atoms quietly change all the time. That fact is worth remembering because it helps place radioactivity in the correct emotional register. It is real. It can certainly be dangerous in high doses or under the wrong conditions, but it is not some supernatural corruption of matter. It is a natural consequence of nuclear stability not being universal. Some nuclei endure, some do not. Some decay slowly enough that they can be present throughout geological ages. Others decay fast enough that they exist only fleetingly unless continuously produced. One of the most beautiful uses of this is in dating the past. Because radioactive decay proceeds with stable statistical laws, certain isotopes become clocks for archaeology, geology, and planetary science. If one knows how quickly a particular isotope decays and can measure how much remains relative to its decay products, one can estimate ages. The bones of ancient creatures, the charcoal of old fires, the cooling of rocks, the history of meteorites, all of these can be read in part through radioactive change. The atom that falls apart is not only a source of energy, it is a witness to time. There is poetry in that, though we need not become too lyrical about it. A nucleus that is not perfectly stable carries within it a measurable chance of change, and from that change we learn how old a fossil is, how long ago lava solidified, how early the solar system formed. The instability of matter becomes a record-keeping system. The universe leaves clocks inside its own materials. At the same time, radioactive decay reveals something humbling about the idea of permanence. Matter can look still and reliable at our scale, yet deep inside some atoms there is a quiet readiness to transform. The stone in a cliff may seem eternal, but within it certain nuclei are changing. The mineral in a wall, the uranium in ore, the carbon in a once-living thing, all of them may carry atomic histories that continue beneath the visible stillness. Once again, the lesson returns. The calm world is built from hidden activity. There are also chains of decay, which make the story even more interesting. A radioactive nucleus may decay into a daughter nucleus that is itself radioactive. That daughter may decay again, and so on through a sequence until a stable nucleus is reached. In such chains, one kind of element turns into another step by step. This is an astonishing thing if you pause over it. For most of history, the elements were thought of as fixed and distinct in an absolute way. And at the chemical level they mostly are. But inside the nucleus, one element can literally become another through radioactive transformation. Lead, radon, thorium, uranium, all can sit in families of descent, turning by lawful stages toward more stable forms. The ancient dream of transmutation was real after all, though not in the simplistic alchemical sense people once hoped for. What drives all of this is the search for a better nuclear arrangement. Too much electrical repulsion, an unhelpful proton to neutron balance, an excited configuration with excess energy, all of these can make change more likely. The atom falls apart because its centre has not found one of the forms that can simply remain. Yet even here, the phrase falls apart still somewhat exaggerates the mood. There is law in the process, not chaos. There are characteristic decay modes, characteristic probabilities, characteristic energies. Radioactive nuclei are not rebellious. They are lawful in their instability. They decay in exact ways permitted by the underlying interactions. If anything, they are too well behaved to be called dramatic. And that lawful instability opens enormous practical consequences. Nuclear medicine uses radioactive isotopes for imaging and treatment. Smoke detectors rely on a controlled radioactive source. Power generation can be built from nuclear processes. Radiation can sterilize equipment and preserve materials. Radioactive tracers can follow chemical and biological pathways. Atoms falling apart are not merely a curiosity of remote laboratories. They have become tools, dangers, resources, and guides depending on how we engage with them. Still, beneath all those uses remains the deeper lesson. The nucleus is not guaranteed. Stability is earned, not assumed. The protons and neutrons at the centre of the atom are held by strong binding, but that binding must compete with internal strain and quantum rules. Some nuclei win that contest indefinitely, or at least for far longer than the current age of the universe. Others lose slowly, others lose almost immediately. Matter is varied not only in chemistry and structure, but in durability at its core, and this durability, or lack of it, is not something classical intuition alone can fully explain. We have already seen probability in electron states and allowed transitions. Now it appears again in the timing of decay. A nucleus may be unstable, yet the precise moment of its decay remains fundamentally unpredictable. That is not just ignorance waiting to be overcome by better instruments. It belongs to the quantum nature of the process itself. The atom does not keep a visible schedule because reality at this scale is not built on visible schedules. It is built on states, possibilities, and transition probabilities. So as the story turns from unstable nuclei toward the deeper character of the atomic world, radioactive decay leaves us with exactly the right kind of unease. Matter is not only made of tiny components and forces, it is made of components and forces that obey rules stranger than ordinary certainty. An atom can remain unchanged for ages and still never possess a predetermined classical moment of decay. It can hold hidden tension at its centre and release it according to laws that are precise in statistics, yet irreducibly uncertain in the individual case. That is the point where the familiar idea of matter begins to dissolve most completely, because beneath solidity, beneath nuclei, beneath light and decay, there is a deeper storm of probabilities and rules waiting to be faced. And that is where the atom stops merely being hidden and starts becoming difficult in a deeper way. Because once we try to describe what is happening beneath matter with perfect ordinary language, the ordinary language begins to creak a little under the weight. We have already met some of the warning signs. Electrons are not tiny planets on neat tracks. Radioactive decay does not happen on a fixed visible schedule. The atom absorbs and emits light in exact portions rather than in a smooth classical way. Protons and neutrons, which once looked like the solid, sensible centre of the story, turned out to be restless bound systems of quarks and gluons. Every step inward has brought us closer to a level of reality where the old habits of thinking do not quite work. This is what I mean by the quantum storm beneath matter. Not a storm in the weather sense, though the comparison helps a little. Not a tidy machine either. A storm is full of pattern and law, but it is not orderly in the way a row of parked cars is orderly. There is movement, uncertainty, structure, and probability all at once. The quantum world underneath matter has something of that character. It is not chaos. It is not nonsense. It is not a failure of science to describe things properly. It is a domain governed by very exact rules that do not resemble the common sense rules we developed from dealing with apples, tables, socks, and doors. That last part is worth remembering because common sense tends to be rather overconfident. It works beautifully in the kitchen, in traffic, while walking downstairs, and in most discussions about whether a cup is on the table or not on the table. It is a splendid tool for the medium-sized world. But it was never trained on electrons, nuclei, or quarks. It was never expected to deal with particles that behave like waves, with probabilities that are not just ignorance, with events that have lawful statistics but unpredictable individual timing, or with objects that occupy quantum states rather than simply sitting in one precise place waiting to be pointed at. So when common sense protests that the quantum world sounds unreasonable, physics is entitled to reply that common sense has had no experience in the matter and should perhaps sit quietly for a moment. The first and most important thing to grasp is that quantum physics is not just a collection of strange stories told to impress undergraduates and ruin dinner parties. It is the framework that successfully describes how matter behaves at small scales. It explains the structure of atoms, the stability of matter, the patterns of light atoms emit, the behavior of semiconductors, the bonding of molecules, the operation of lasers, the decay of unstable nuclei, and a truly alarming amount of modern technology besides. The quantum world is not optional decoration. It is how the interior of matter actually works. Even so, it remains hard to picture. That is because the quantum world is not built to be pictured in the same way the everyday world is. We like to imagine objects as having definite positions, definite motions, definite properties whether we are looking or not, and causes that unfold like visible clockwork. The quantum world does not always offer that kind of comfort. Instead, it offers states, amplitudes, probabilities, and rules for what can be observed when a measurement is made. This does not mean nothing is real until someone comes along with a laboratory coat and a clipboard. It means that reality at this scale is not classical reality in miniature. Take the electron in an atom. We have already said it is not best described as a tiny bead orbiting the nucleus. The better description is a quantum state that tells us where the electron is likely to be found if we measure it. That likelihood is not just a practical shortcut because we are too lazy to look harder. It is built into the way the theory works. Before measurement, the electron is described by a spread of possibilities. That does not mean the electron is making up its mind. It means the world at that scale is described by a mathematical structure richer and stranger than the one our ordinary imagination prefers. This is usually the moment when people ask whether quantum mechanics is saying that particles are in many places at once. The safest answer is yes, in the sense that the quantum state can include multiple possible outcomes or locations, but with the important warning that this phrase is useful only up to a point. It helps break the grip of classical thinking, but it can also mislead. The electron is not literally smeared like butter across bread, nor is it secretly darting about so fast that we merely fail to pin it down. The better statement is that the electron is described by a quantum state whose probabilities can extend across a region, and only when a measurement is made do we obtain a definite outcome. The theory predicts those outcomes with extraordinary success, but it does not let us replace the whole thing with a tidy hidden little orbit and call the job finished. There is another consequence of this that makes the quantum world feel even more unlike the ordinary one. Certain properties cannot both be pinned down with arbitrary precision at the same time. Position and momentum are the famous example. The more sharply one is defined, the less sharply the other can be. This is not because our instruments are clumsy or our hands are too large for the task. It belongs to the structure of the quantum world itself. Matter at the smallest scales is not built from particles carrying around perfectly definite classical information in every respect at once. There are fundamental limits to what can be simultaneously specified. That can sound irritatingly philosophical until one notices how much it matters for the existence of the world. If electrons in atoms could simply sink into the nucleus with precise classical stillness, atoms would not have the stable sizes they do. Quantum uncertainty, along with the allowed structure of electron states, helps prevent matter from collapsing into a much duller and less useful form. The atom is not stable despite quantum rules. It is stable because of them. The storm is not a problem that ruins matter. It is the reason matter survives. This is one of the recurring surprises in the subject. The very features that sound unsettling are often the ones that make the world livable. Uncertainty sounds like disorder, yet it helps sustain atomic structure. Probability sounds like weakness, yet it yields predictions of astonishing accuracy. Wave behavior sounds vague, yet it gives rise to the exact allowed states that explain chemistry and light. The quantum world is strange, but it is not sloppy. In fact, it is often stricter than common sense, only in a language common sense did not invent. Another concept that deserves careful attention is superposition. This is the idea that a quantum system can exist in a combination of different possible states until a measurement produces a definite outcome. Again, one must handle the language gently. It is very easy to slip from useful explanation into nonsense here. Superposition does not mean that nature has abandoned reality and become purely symbolic. It means that the quantum state can include several possibilities at once in a physically meaningful way, and those possibilities can interfere with one another like waves. That interference is not a metaphor. It produces real measurable consequences. The famous double-slit experiment is perhaps the most dramatic demonstration of this. When particles such as electrons are sent toward a barrier with two openings and then detected beyond it, they produce an interference pattern characteristic of waves, even when sent one at a time. It is as though each electron explores the available possibilities in a way no classical particle should. Yet when a specific measurement of path is made, the behavior changes. The pattern depends on what kind of information is available about the system. Few experiments have done more to persuade physicists that the quantum world must be taken on its own terms, rather than forced back into classical language at all costs. There is something deeply unsettling and deeply beautiful in that. The electron is not just an object moving from point to point in the old way. It behaves according to a quantum state that can interfere with itself. Matter carries within it a capacity for possibility that has no good classical analogue, and from that capacity come the patterns, the states, and the stable structures on which the visible world depends. Once superposition is allowed, measurement becomes one of the great conceptual puzzles. What exactly happens when a quantum system yields a definite outcome? Different interpretations of quantum mechanics offer different ways of understanding this, and physicists have debated the matter for generations with admirable persistence and only occasional despair. Some views emphasize collapse of the quantum state upon measurement. Others treat the evolution differently and place the weight elsewhere. What matters most for our present purpose is not choosing among interpretations, but recognizing the core fact. Quantum systems are described by a spread of possibilities, and measurement gives specific results according to well-defined probabilities. That means nature at this level has an irreducible element of chance in how individual events turn out. Not chaos, not anarchy, not a universe flipping coins because it has misplaced the manual. Rather, a world in which the probabilities themselves are exact and lawful, while the specific outcome of a single event is not predetermined in the classical way. One radioactive atom decays now, another later. One electron is detected here, another there, even though the overall distribution follows the theory precisely. The law is statistical and exact. The individual event is not classically scripted. This can feel like an assault on the old dream that if only we knew enough, we could predict everything perfectly. That dream belongs to classical physics at its most confident. In such a universe, complete knowledge of the present would in principle yield complete knowledge of the future. The quantum world modifies that dream quite severely. Even with the fullest possible quantum description, what one often gets are probabilities for outcomes rather than a single inevitable future path. Nature does not owe us clockwork, and still, the atom works, the world holds together, solid matter exists, stars shine, life evolves, all while the foundation of matter is built from quantum states, uncertainties, superpositions, transitions, and probabilities. That is perhaps the most astonishing part. The strange world is not hiding in some remote corner beyond practical relevance. It is the actual basis of everything around you. The ordinary world is what the quantum storm looks like when averaged, stabilized, and scaled up. That scaling up matters enormously. Individual quantum systems can behave in strikingly delicate ways, but large collections of particles usually do not display their quantum strangeness in direct, obvious form at our scale. Interactions with the environment tend to wash out the fragile coherence of certain quantum states. The technical details are subtle, but the broad point is easy to appreciate. A single electron can display quantum interference in a controlled experiment. Your pillow, thankfully, does not typically do so in a way that requires you to reconsider bedtime as a probability distribution. The macroscopic world emerges from the quantum world, but not every quantum feature remains visible in the same form once countless particles and environmental interactions are involved. This is why the world feels classical most of the time. Objects seem to have definite positions. Cats remain in one place long enough to ignore you effectively. Cups do not occupy visible superpositions across the kitchen counter. The deep quantum structure is still there, but the large-scale world has settled into robust patterns where ordinary descriptions work beautifully. So the quantum storm beneath matter does not mean daily life becomes unusable. It means daily life is the stable surface phenomenon generated by deeper rules. There is a useful comparison here with water. At the human scale, waves, currents, and tides can be described meaningfully. But water is made of molecules, and molecules are made of atoms, and atoms are quantum systems. None of those deeper facts makes the tide unreal. They explain how the tide is possible. In the same way, the chair remains a chair, the stone remains a stone, and your hand remains your hand. Even though each is ultimately built from matter governed by quantum rules, no piece of furniture ever bothers to explain to its owner. And the rules go further still. Quantum tunneling is one of the most remarkable examples. In classical physics, if a particle does not have enough energy to cross a barrier, it cannot cross. End of discussion. The barrier says no, and the particle must accept the decision. In quantum physics, the situation is more subtle. There can be a probability that the particle appears on the other side of the barrier, even when classical reasoning would forbid it. This is tunneling. It sounds impossible only because classical intuition has been allowed too much authority. In the quantum world, the wave-like nature of particles makes such effects real. Tunneling is not a minor curiosity. It matters in radioactive alpha decay, where part of the reason an alpha particle can escape the nucleus is that quantum tunneling allows it to get through a barrier it could not classically surmount in the usual way. It matters in fusion in stars, where positively charged nuclei can approach close enough for the strong interaction to take over, thanks in part to tunneling despite their electrical repulsion. Without this, stars like the Sun would have a much harder time doing the work they do. It matters in certain electronic devices and in many other processes besides. Once again, the strange rule is not a decorative mystery. It is an active part of how the universe functions. One begins to see a pattern here. Every time the quantum world offers a feature that sounds unreasonable, it turns out to be essential somewhere. Uncertainty supports atomic structure, superposition, and interference shape electron behavior. Probability governs decay and measurement outcomes. Tunneling makes nuclear processes and stellar fusion possible. The world is not merely tolerant of quantum strangeness, it is built on it. There is also the question of whether particles are really particles at all in the old sense. Modern physics often describes the fundamental ingredients of reality in terms of fields, with particles appearing as quantized excitations of those fields. This is conceptually deeper, and in many ways more accurate, but also more difficult to picture in a sleepy human brain at the end of the day. The important point is that the most successful descriptions of matter do not reduce to tiny hard objects rattling in empty space the way early imagination once hoped. They involve fields, states, interactions, and quantized excitations. The language of little billiard balls simply does not go deep enough. Yet for all that sophistication, one should not lose the thread of the story. The atom is what it is because the quantum world beneath matter allows only certain states, certain transitions, certain combinations, and certain outcomes with certain probabilities. That is why electrons occupy orbitals rather than arbitrary paths. That is why atoms emit precise spectral lines. That is why some nuclei decay and others do not. That is why solids resist, molecules bond, and semiconductors behave in their intricate, useful way. The quantum storm is not a separate, deeper subject hiding underneath the atom. It is the atom's inner logic. This can even reshape the way one thinks about reality itself. In the classical imagination, the world is made of objects carrying properties that remain there in a straightforward way whether or not we look. In the quantum imagination, the world is made of systems described by states that determine probabilities for what can be observed. That does not make reality less real. It makes realism more subtle. The universe still exists. The atom still exists. Your bed is still performing valuable work, but what exists is not always best described by the old language of small, hard things with fully determinate classical stories. There is a certain humility in accepting that. Science is at its best when it lets reality teach it how to speak. The quantum world forced physics to become more modest and more ambitious at the same time. More modest because it had to give up some cherished intuitions. More ambitious because it built a new mathematical and conceptual framework capable of describing matter far more accurately than old common sense ever could. The result is not a perfect picture one can hold in the mind like a toy model. It is something better. It is a theory that works again and again, even when its meaning continues to provoke argument. And perhaps that is exactly right. If the foundation of matter were simple in the old visual way, there would be little left to wonder about after the first few lessons. Instead, the world kept its depth. Beneath every object lies atomic structure. Beneath atomic structure lies quantum behavior. Beneath what feels solid lies a framework of probabilities, states, and interactions, so unlike daily life that the entire visible world becomes more impressive just for existing so calmly on top of it. So when you hold an object, or rest against a pillow, or look at the dull painted wall across the room, you're not leaning on certainty in the classical sense. You're leaning on a vast settlement reached by quantum matter under reliable laws. The calmness you experience is real, but it has been assembled from something far more active, delicate, and strange than the senses ever report. And once that becomes familiar, the final step in the journey is not to go smaller still, but to step back and look again at the whole arrangement, the tiny theatre inside everything, where all these hidden actors together produce the world that seems, from a distance, so simple. So here we are at last with the whole arrangement in view again, and what a strange arrangement it has turned out to be. We began with the ordinary impression that matter is simply there. A wall is a wall, a cup is a cup, your hand is your hand. The room seems full of things that are solid, calm, and finished. That is how the world presents itself, and for getting through the day it is a perfectly useful presentation. You do not need a course in atomic physics every time you sit on a chair. The chair does not require that kind of emotional labour from you, and for that we may all be grateful. But once you begin to ask what is happening inside matter, the familiar world opens in a very different way. The chair is no longer just a chair. It becomes a structure made from atoms. Those atoms are not tiny solid beads. They contain a dense nucleus and a strange outer region shaped by electrons. The nucleus contains protons and neutrons. The protons and neutrons contain quarks. The whole thing is held together by forces that work differently at different scales. And beneath all of it runs the quantum behaviour that makes the entire arrangement possible. What is so pleasing about this is that nothing in the room had to change for the room to become more interesting. The pillow beneath your head did not grow brighter or start giving a lecture. The wall did not politely step aside and reveal a glowing diagram. Matter remained exactly where it was. The change happened in understanding. Once you know a little about what happens inside an atom, ordinary life acquires a second layer. Not a mystical one, not a sentimental one, just a more informed one. The world becomes denser with explanation even while it looks exactly the same. That is why I think of it as a tiny theatre inside everything. Not because there are little actors in costumes performing a drama for your benefit, though one suspects electrons would be difficult to cast and quarks would be impossible to keep on set. I mean that every ordinary object contains an unseen interior performance. There is structure, there is tension, there is energy, there are roles being played. Electrons occupy allowed states and shape how atoms interact with one another. Nuclei hold themselves together through a careful balance of forces. Some nuclei remain steady for ages, some quietly change. Light is absorbed, light is emitted, matter resists, matter bonds, matter decays. All of that hidden activity produces the stable, useful stage set of everyday life. And the remarkable thing is that this theatre does not happen in rare, special places. It is everywhere. Not only in stars and laboratories and textbooks with ambitious diagrams. It is in the glass by the bed. It is in the fabric of the blanket. It is in the air that moves in and out of your lungs. It is in the paint on the wall. It is in the water in a pipe. It is in your bones, your skin, your blood, your nerves, your eyes. The atomic world is not tucked away in some separate scientific district of reality. It is the actual interior of the familiar world. That can be a comforting thought, in a slightly unusual way. The universe often feels remote when described at its largest scales. Galaxies are beautiful, certainly, but they are not much help when you're trying to understand the cup in your hand. Black holes are impressive, but they do not explain why the spoon remains spoon-shaped, or why the lamp glows, or why the table resists your elbow. The atom brings the mystery home. It tells you that the deep strangeness of physics is not only out there, it is here, quietly supporting the ordinary. The word quietly matters. Because for all the strangeness we have uncovered, the result is not confusion in practice. Matter works. Atoms are strange, but they are reliable. Electrons follow quantum rules that sound slippery in description, yet those rules are precise enough to make chemistry possible and stable enough to build every material system around you. Nuclei are compact and tense, and sometimes unstable, yet stable enough nuclei exist in abundance to form planets, oceans, mountains, bloodstreams and brains. Quarks are confined inside protons and neutrons in ways that defy ordinary intuition. Yet the larger particles they form are dependable enough to become the building blocks of atoms. The hidden world is not chaotic. It is disciplined. It simply happens to be disciplined in ways that do not resemble common sense. That may be the most important thing to carry away from the whole journey. Strange does not mean sloppy. Quantum does not mean random in the lazy everyday sense. Unseen does not mean vague. The atom is not mysterious because science has failed to understand it. It is mysterious because science has understood enough to discover that reality at this scale is genuinely unlike the pictures we first expected. And yet those deeper rules are exact enough to explain the world with extraordinary success. In fact, the world you know depends on that exactness. Take something as ordinary as the pressure of a mattress supporting you. At human scale, it feels simple. Weight presses down, the mattress pushes back. End of story. But of course, that is only the summary version. Underneath it are atoms arranged in materials, electrons shaping chemical bonds, molecular structures giving the mattress its flexibility, electromagnetic interactions preventing matter from collapsing into itself, quantum rules governing what states particles may occupy, and a great many organised consequences of all that microscopic behaviour. Even rest turns out to be built from activity. That is true of nearly everything around you. The hardness of metal, the softness of cloth, the brittleness of ceramic, the smell of rain on dust, the colour of leaves, the transparency of glass, the conductivity of copper, the warmth of skin, the glow of a filament, the way a book page bends but does not dissolve in your hands. None of these are simple properties sprinkled onto objects from outside. They arise from the internal architecture of matter. The tiny theatre is always performing, and the large-scale world you live in is what the performance looks like from the cheap seats. There is also something very reassuring in the fact that this hidden world is shared. The same atomic rules apply whether the atom is in your body or in a stone or in a distant star. Hydrogen behaves as hydrogen here and there. Carbon remains carbon. The electron does not adopt one personality in a laboratory and another in a cloud. This consistency is one of the reasons science can know anything at all. The universe is not improvising the basic rules from place to place. It is astonishingly dependable. That's why spectroscopy can read stars, why chemistry can be taught, why semiconductors can be engineered, why medicine can use radioactive tracers, why clocks can be built from atomic transitions, why the whole practical enterprise of modern physics works. The tiny theatre may be hidden, but it is not whimsical. Still, it does not become less strange just because it is dependable. I think that is part of the charm. The atom gives us a world that feels solid even though solidity is not what it first seemed to be. It gives us stable matter even though its foundations involve probability and uncertainty. It gives us light through exact transitions between invisible states. It gives us elemental identity through proton count, mass through nuclear structure, and a deeper level of composition through quarks and gluons. It gives us a visible world that makes sense at our scale, while being built from ingredients that absolutely do not behave like tiny classical pebbles. Nature could have chosen a much duller arrangement. Instead, it built reality in layers, and those layers matter because they explain why the world has both simplicity and depth at once. At one level, the room is just a room. At another, it is chemistry. At another, it is atoms. At another, it is nuclei and electrons. At another, it is quarks, fields, and quantum states. Each level is real in its own way. None of them cancels the others. The ordinary description is not false because a deeper one exists. It is incomplete, but that is not the same thing. You do not stop calling water water because you know about molecules. You do not stop calling a person because cells are involved. And you do not stop calling a table because inside it lies an astonishing history of atomic order. That layered view helps with another question people often carry quietly in the background. If matter is mostly empty in one sense, if electrons are probability distributions rather than little orbiting beads, if nuclei can change and quarks cannot be isolated, then is the familiar world somehow less real than it seemed? The answer is no. It is more structured than it seemed, not less real. A table is not an illusion because its solidity emerges from electromagnetic resistance and quantum rules. A rainbow is not unreal because it depends on optics. Music is not unreal because it depends on vibrating air. Explanation does not subtract reality. It adds detail. This is a useful thing to remember any time physics starts to sound as though it is taking the world away. It is not. It is giving the world back in higher resolution. The cost is that the higher resolution is sometimes harder to picture, and occasionally a little rude to our intuitions, but the gain is enormous. Suddenly, the ordinary object becomes a successful solution to many deep problems all at once. It holds together, it has shape, it has colour, it interacts with light, it resists your hand, it survives through time, it may carry atoms that were forged in ancient stars, it may contain nuclei that have remained stable since before life emerged on Earth. The humble object becomes a compressed history of physics, and once you notice that, the boundary between the dramatic and the ordinary starts to blur. A star sounds dramatic, a spoon does not. Yet the spoon contains atoms whose heavier elements were once made in stellar furnaces or explosive cosmic events. The star sounds grand, and the spoon sounds domestic, but in substance they are connected by the same physical story. The spoon is not a lesser object. It is simply the quiet phase of the same universe. That quiet phase is what makes the atom such a good subject for slow thinking. It is easy to be impressed by violent things. Explosions, black holes, supernovas, great bright events in the cosmos. The atom offers a different kind of amazement. It asks you to be impressed by steadiness, by the fact that matter can be both strange and useful, by the fact that the world can be made from probabilities and still support a bookshelf, by the fact that electrons do not need tiny tracks in order for paper to feel dry and ceramic to feel cool, by the fact that the deep rules of reality can be weird without making daily life impossible. This is a quieter kind of wonder, but I think it lasts longer. And perhaps that is why returning to ordinary objects after a journey through atomic physics feels so satisfying. The object does not seem reduced. It seems enriched. The glass becomes more than glass. The blanket becomes more than blanket. Your own hand becomes more than a convenient tool for holding mugs and opening doors and occasionally knocking things off tables by accident. Each is revealed as a stable arrangement of matter with an interior life too small to see and too lawful to ignore. Your hand is a particularly good example because it is both the thing doing the touching and itself a touch thing in the universe. It feels the world because of nerves, chemistry, and biological structure, but it is also made from the same atoms as the world it feels. The hand and the table are not made of separate categories of reality. They are arrangements of the same deep ingredients. When your fingers rest on a surface, one part of atomic matter meets another part of atomic matter, and the result is sensation, pressure, warmth, texture, resistance. A human experience emerges from physical structure. That is not a small achievement. None of this requires us to become solemn about matter, though physics certainly tempts people in that direction. It is perfectly acceptable to retain some lightness. The atom is one of the great examples of the universe being much more complicated than absolutely necessary. A simpler design might have done the job. Instead, we get quarks inside nucleons, inside nuclei, inside atoms, inside molecules, inside materials, inside living systems, wondering what all the fuss is about. It is gloriously overbuilt. There is almost a sense that nature enjoys depth for its own sake. And maybe that is why learning about the atom never really feels finished. Even after you know the basic structure, the forces, the light, the decay, the quantum rules, there is always another question nearby. How do many atoms behave together in solids? How do these principles scale into life and consciousness and memory? How does the quantum world connect to gravity at the deepest level? Are quarks truly fundamental, or is there another trapdoor waiting? The atom answers a great many questions, but it also improves the quality of the next ones. For now, though, it is enough to let the picture settle. Around you are objects that seem still. Inside them are atoms. Inside those atoms are nuclei and electrons. Inside the nuclei are protons and neutrons. Inside those are quarks held in fierce confinement. All of it governed by forces and quantum rules that never appear directly in ordinary sight and yet shape every ordinary experience you have. The world feels simple because it is good at presenting a finished surface. Underneath that surface, the tiny theatre never stops. So if the room seems quiet now, that is only the large-scale version of quiet. The deeper version is busy in a very disciplined way. Electrons remain in their allowed states until disturbed. Atomic bonds hold. Nuclei endure or slowly change. Light is absorbed and emitted. Materials keep their shape. Your body continues its chemical work without demanding applause. Matter performs itself constantly and mostly without complaint. And the more one thinks about that, the less empty the world appears. Not crowded in a noisy way. Crowded with structure. Crowded with hidden order. Crowded with events too small to notice and too important to do without. Which leaves us very gently back where we started, with the nearest object, the nearest surface, the nearest breath, the nearest ordinary thing. Still looking ordinary, of course, still doing its job, but no longer simple, not really, not once you know what has been going on inside it all along.